Record. Okay. No, I don't mind talking about that stuff at all because it's, all of this is applicable. Whether or not it's directly applicable to everybody's experience, these are all things that, this is what makes ham radio unique, where if you look at transmitters, right? Transmitters have to meet spectral purity requirements. When we go and buy something, the assumption is that, in the big sandbox of all these frequencies, we're not, that what we bought is not going to interfere with anybody else, right? That's one of the rules. So when you go and buy something, the assumption is that whoever designed it and built it and you paid for it from them, they did their job. And if something goes wrong, it's not your fault, it's their fault. In this case, your license gives you the ability to basically do exactly what they did, which basically means if something goes wrong, ultimately it's your fault, which is again why it's important to go through, the licensing process. Not that you're going to be perfect about it, not that you're going to understand everything, but at least you're going to know that these rules exist and that you do have to follow them. So yeah, I mean, anything that comes up like this, I would say is an applicable discussion, and don't feel bad about asking. All right, so let's see. Yesterday we made it through safety, and now we're into RF hazards and radiation exposure. And so this is not radiation as we think of like nuclear radiation, but this is what we call non-ionizing radiation. Radiation is just it's just basically electromagnetic energy in this case. It's photons, just like gamma rays and X-rays, except that again, we're at much, much lower levels of energy, right? Radio waves are actually very low energy, much lower energy than light and stuff like that. So this is non-ionizing radiation. Let's say a radio wave hits your body. It doesn't have enough energy to actually do any cellular damage. It can't do anything to your DNA. Microwaves, for instance, can heat up water, which can warm up your insides a little bit. So, oh, and I just got a note. Is Megan here?
Yes, hi.
Hey, okay, so this I just got a note that says you need to finish your exam agreement.
I thought I just hit submit.
Oh, did you just do it?
Like within the last 5 or 10 minutes, yeah.
Okay, good, because he sent it 15 minutes ago. Okay.
Okay.
I think it's probably done then.
Let me know if they say anything else in like
Okay.
an hour or so if I have to go back and check.
Okay. All good. All right. Let's see. So in order to ensure that we don't cook anybody or anything, we have to meet certain requirements as far as making sure we don't have enough RF energy around to actually hurt anyone. So we can follow, if we follow the rules, the station licensee, who's the person responsible for the station, is responsible for doing an RF energy exposure study to make sure that nobody is exposed to excess levels of RF energy. And that could also include, putting up signage or putting up fences, things like that. But part of it is actually going through and verifying that all the numbers are met. So the first thing to do there is take a look at all the equipment you have, figure out where your antennas are. And well, then you can do this thing called FCC OET Bulletin 65. Nobody wants to do that. You can also do computer modeling. That actually gets pretty complicated. You can actually walk around the site with a calibrated field strength meter. I don't know many people who have those. So the easiest way to do it is assume that we're going to be talking about worst case scenarios. Worst case scenarios are always great. And so we're going to go to a website called that somebody has put up, which basically took all the FCC rules and put them in a simple calculator. I'm going to put this out in the chat because it's really useful. And And what this does is, oh shoot, gotta unshare that one and share this one instead. Here we go. Okay, this says, what's my average power? That's time averaged power. So let's say we're going to be putting out 25 watts. The antenna gain in dBi. Notice the difference between dBi and dBd. So that's decibels with respect to an isotropic or a dipole. So let's say we just have a dipole, so we have 0 gain. Well, in dBi, it'd be 2.2, let's say. Distance from the area to the distance from the area of interest to where the people are in meters, let's say 10 meters away. And we're operating at, let's say 28 megahertz, and include the ground. Yes, there we go. Okay, so the estimated RF power density in milliwatts per square centimeter. This is basically an RF flux that exists in space at that distance, given that antenna and that power level and that distance to people, is way down here. And the difference between a controlled environment means everybody in the area knows what's going on. An uncontrolled environment means you just have the general public walking through. So you can see that if this is what the estimated power density is, these are the limits for uncontrolled. We typically go with uncontrolled. So we are well within the safety limits. So basically you do this, you run it through, you run the numbers, you print it out and you put it up on the wall and everything's good. If you change a transmitter or change an antenna or change your feed line, because if you have, notice this says average power at the antenna, that might be your transmitter power. But if you have lossy cable, well, then your average power is actually going to be lower. So anyway, all right, moving on. The definition of duty cycle. Duty cycle is the percentage of time that your transmitter is transmitting. So if I'm transmitting 50% of the time and I'm listening 50% of the time, my duty cycle is 50%. What duty cycle allows us to do is it gives us a time average. So if I'm transmitting for 50% of the time at 100 watts, then my average, well, when I'm transmitting, it's 100, but it's only half the time. So my average is only 50 watts. So what that allows me to do is it allows me to, for instance, if we know that it's going to be safe, if I transmit 100 watts 100% of the time, I could transmit 200 watts for half the time and 0 watts for the other half of the time. Why do exposure limits vary with frequency? And that's because the human body is not just a brick. The human body has a size and a resonance, and we absorb more energy at some frequency than others. And for whatever reason, the 6 meter band is about the peak of our absorption of RF energy. So that would be the 50 megahertz, the 6 meter band. What factors affect the RF exposure of people near an antenna? Frequency and power level, distance from the antenna to a person, and radiation pattern of the antenna. Again, if you have a dish antenna that has 30 dB of gain and you're standing behind the dish, you're going to have a very different experience than if you're standing in front of the dish. If you have how to reduce exposure to RF radiation, you can move the antennas somewhere else. You put them 30 feet higher, they're 30 feet further away from everybody, and the exposure level goes down. And if you ever change any equipment at all, or antennas or cable or anything, you go and do another evaluation. And fortunately, it's actually pretty simple. Okay, so we are on the 77th page of the book. So why should you use short and heavy gauge wires? And this comes back to whose law again, everybody?
Ohm's law.
Ohm's law. Okay, so let's say that I have a battery, which is 12 volts, and I have a cable, which is no longer a perfect cable connecting to our load. This is our transmitter. And our load is going to be, let's say, 100-watt transmitter. At 100 watts, we're going to say that this is nominally will operate at 12 volts. And if we say E equals I times R, what we'll find is what is, and P equals I times E, we could find an equivalent resistance for it, but really what we need is to figure out the current. I is equal to P divided by E is 100 divided by 12, and that gives us about 8.3 amps. Now, if you could somehow manage to run a 100-watt transmitter from an 8.3 amp power supply, I would love to hear how you do it. This doesn't work. Typically, that transmitter is going to draw about 20 amps. So why is it going to use 20 amps of power or 20 amps of current, which would turn into 240 watts to put out 100 watts? Let's hear some ideas.
Well, you've got to power the receiver, you've got to power the gauges and dials and all
Yep.
the
Yep.
stuff that supports the radio itself.
Right? That's a big one. How about another one?
You've probably got RF losses and things.
Yep. But you've also got this thing called efficiency. So basically what you're looking at is that a typical amplifier is somewhere between 50 to 70% efficient, depending on how you're operating it. Which means that if you put a certain amount of power in, you're only going to get between 50 and 70% of that power out as radio frequency energy. So that is why if we have a 100-watt transmitter, we would typically have about 200 watts in. And then our efficiency would be power out divided by power in, which in this case is 50%. And that's actually pretty typical. And that's why for a 100-watt transmitter, you typically have at least a 20 amp power supply. So once we've established that, oh, darn it, I grabbed the wrong thing again. I got to stop doing that. Why does it keep moving? There we go. Okay, so which of the following is an appropriate power supply for a 50-watt transceiver? And that would actually be 12 amps. So that's, 140, 150 watts to run a 50-watt radio. And that's, again, because of efficiency. Now, here's the other one. We're going to talk about Ohm's law. So let's say that we have a power supply running at 12 volts, DC, and here's our load, which is our radio. And it requires 20 amps to run this radio. Okay, we're going to just do a basic calculation on this right here. So if we assume that all that wire is replaced by basically a resistor, we can do Ohm's law to say V or E equals I times R and P equals I times E. So if we have a perfect wire, what is the resistance of a perfect wire?
Should be 0.
Should be 0, but we don't have a perfect wire. Let's say that we have a piece of wire that looks like this, and it has a length, and it has an area. As it gets longer, its resistance goes up. As it gets smaller, its resistance also goes up. It's kind of like squeezing water through a smaller and longer pipe. So what ends up happening is that those things, so as the length goes up, the resistance goes up. As the area goes down, the resistance also goes up. So then what we end up with is a resistor that is not 0 anymore, because we no longer have a perfect wire that doesn't exist. So we can take this wire And we can say that every part of this wire is perfect, except that we're going to add a lumped resistor right there, a single value. And we're going to call this value R. So if I have a current flowing through a resistor, what is the voltage in the resistor by Ohm's law, everybody? What does Ohm's law say? Ohm's law is what?
E equals IR.
E equals IR. Okay, so we can say that if this resistor in this case is 0.1 ohms, which is a pretty low resistance, I think everyone will agree. We can do E equals I times R. Well, we have a current of 20 amps. We already said that. And 20 times 0.1, how many volts is that?
2.
2 volts. What was our power supply to begin with? That's 12
Well.
volts. If we burn up 2 volts in that resistor, which is that wire, how many volts are left? For
10.
10 volts left. What will happen is when you transmit and your voltage goes down to 10 volts, that will typically not be enough voltage to keep the power, to keep the control circuitry turned on, and the radio will suddenly do what?
Stop.
It'll shut off. Yeah, the power, it'll actually turn off. And that is why it's really important to make sure that you have wire that is as short as possible and as thick as possible to keep your IR loss, as it's called, to a minimum. That's basically voltage drop. That's called voltage drop. And that's why, again, you know, you might find that a radio that's rated for 20 amps, it has like number 8 wire, which is rated for 40 amps. And, you know, they say cut off the excess. And the reason you cut off the excess is because you want to minimize your voltage drop. And that's the same reason why we don't, for instance, use, for the most part, the cigarette lighter in your car. Number one, it's not designed to handle that much current. And number two, we don't really know how they wired it. You know, I mean, if it's only designed to run, if it's only designed for 5 amps and you try to pull 20 amps through it, you may or may not blow a fuse, but at the same time, it may also only be like 18 gauge wire, in which case it's going to be really, really lossy. You're going to lose a lot of voltage getting to your equipment. It might not work. Okay, another one. All right, so now we're talking about digital communications and connecting a computer to a radio. Okay, so if we think about what a radio requires, how do you get your voice into a radio?
It's a microphone.
Microphone. Okay, so that can look something like this, right, with a push to talk button. And how do you listen to what's coming out of a radio?
Through a speaker.
Through a speaker, right? Okay, so now we have a computer. How do you get voice into a microphone or into a computer? Well, you can have a headset, and the headset will typically have a microphone. And how do you hear what's going on? You have a headset, right? You can hear what's coming out of the speaker. Both of those things have to be connected. So if we want the radio to basically replace the computer, or the computer to replace the radio, as we want to think of it that way, we can basically do this, and we can do this. And one part of the computer, which was the headphones, goes into the microphone input of the radio, and the microphone input of the computer goes to the speaker port of the radio. We basically just have the computer replacing you, or the radio replacing you, depending on how you want to think about it.
And do you have to match impedances with these things as well?
Typically, yeah. But typically you're not going to have that bad of a mismatch. You know, they'll often work, but you might have an impedance match to deal with. Now, the only other thing is, how do you normally make a radio transmit? There's usually a
Push
little
to-
button
push to
somewhere.
talk.
It's
Yeah,
called push to talk, right? And that's usually on the microphone. But where's the push to talk button now? We took it away. So what happens is that you have to have some way for the computer to key the push to talk line. So if your computer is going to be talking through if your computer is going to be sending information through the radio, you have the speaker jack of the radio connected to the microphone input of the computer and vice versa. And then you have something running a push to talk line. One thing that has happened recently is that we have a lot of radios that actually have something called CAT control, which is a computer aided transceiver. And CAT control basically allows this radio to be controlled by this computer using a special, or in some cases, just a USB cable. So all the functionality is done through a USB cable, which is really, really helpful. Another thing that's cool about this is that a lot of radios actually have a sound card built in. So if you connect up that USB port, not only does it do the CAT control, it also connects a sound card at the same time. So the audio that normally would go through the headphones and the speaker jack and stuff like that is now completely controlled through a USB cable. And this is actually what I have with my 7300. My 7300, it does CAT control and USB audio, sound card through a single cable. Makes it a lot easier. Works very, very well. Of course, then you have to become an expert at Windows to make sure that it works right, or a Mac or whatever computer you happen to be using. Okay, so digital mode operation, you have receive audio, transmit audio, and transmitter keying. If you're running FT8, FT8 again is a digital mode. So you have to have the audio signals and input and output, and then a computer running WSJTX software. So essentially it handles all the audio processing, typically through a USB cable. Now, some radios, for instance, my Yaesu FT817, which is what I take on the road with me, it does not have a sound card. So I basically, you can build it, you can buy it. Essentially, this is an outboard sound card. Here's your computer. This connects via USB from the computer to the sound card. This sound card then becomes a part of the computer system and connects to the radio using your mic input and your speaker output, and also handles the PTT. And not to worry, they're not particularly expensive if you want to buy one. The simplest one that works really well that I've used for years, and so have lots of other people, it's actually made right here in Grants Pass, is known as a Signal Link USB. And this basically is an external sound card that allows you to interface basically any radio, no matter how old, to a computer. Okay. Let's see. We'll skip over that. It's basically more of the same. Okay. Which of the following can you use to cure distorted audio caused by RF current on the shield of a microphone cable? Okay, so now we're going to talk about RF energy and RF current and how RF current behaves differently from what we think of as current. Okay, so we're going to draw this piece of wire. If we have DC current, DC basically distributes as it flows throughout the entire conductor. AC, on the other hand, flows on the outside, only to a certain depth. And actually that depth is inversely proportional to the frequency that you operate on, which basically means if you're operating at RF frequency, nearly all of your energy is actually flowing on the outside edge of the conductor, not on the inside, which has some interesting implications, because let's say that you have you have the exact same amount of copper and you have something you can pound flat, right? You can take a certain amount of copper and pound it flat, or you can leave it round. Which one gives you the most surface area? Something that's pounded flat. So it turns out that a flat strap is actually much better at carrying RF energy than something that's round because of the skin effect. Now, this is not to say that all of your cables should be replaced by, by pieces of flat cable. That is not true. But if you are doing things like grounding and you want to, let's say we covered this a little bit yesterday. So here's my transceiver, my XCVR, and here's my, what I would call ground. And you have something that goes from here to here. And you want to have a low impedance path for RF energy that might appear on your transceiver on the case to get to ground. You want the lowest impedance path available. And the lowest impedance is presented by a flat strap, which is why a lot of people for grounding, they don't use round cable. They actually use strap, like a flat piece of conductor to handle their grounds. Okay. Another one is distorted audio caused by RF current on the shield of a cable. Okay. So this is another interesting topic. Now, where did I just say that the current flows on a piece of cable?
The skin.
On the outside. That's right. Okay. So now what I'm going to do is draw a piece of coaxial cable. Here's the center conductor. And here's the shield. Okay. So this is metal, right? This is typically aluminum or copper or something. This is another conductor. So that's our center conductor that carries some of the RF energy. How many surfaces are there in this case? How many electrical surfaces do you see?
I see 3.
There are 3. There is 1, there's 2, and there's 3. 2 is on the inside and 3 is on the outside. So believe it or not, the shield of a coaxial cable can actually carry 2 completely independent currents, one on the inside of the cable and one on the outside of the cable. Well, if we do it right, the inside of the cable is going to match what's on the center conductor. Well, we did not intend to put anything on the outside of the cable. It just happened to show up because any piece of wire can act as an antenna. So what we tried to do in this case, you could have, let's say, here's your transceiver, and your transceiver goes to a microphone, your transceiver goes to an antenna, and your antenna is transmitting RF energy everywhere. And here's your microphone. I'll make a little old school astatic lollipop microphone. Good old classic microphone. And this is connected to the transceiver by a cable. Well, every cable is what? Any piece of wire can function as what?
Antenna.
An antenna. Okay. So that means that this RF energy, which is flying around in space, some of it could happen to couple into the microphone. Well, if that's true, then you have RF energy, which is getting into the microphone and conceivably is getting back into the transceiver, which is very, very bad. It causes all kinds of distortion. So we can take a look at the outside of a shielded cable and we can actually prevent against that. So if we were to look at a single wire, right, we're going to ignore whatever's inside. And we take this has, as current flows, we have a magnetic field that zips around the wire. So if we do something to this wire, and we can do like this with it, and we can use a material to build a magnetically absorbing circuit. All the magnetic field that gets generated by the flowing current tends to get absorbed in this device. And this is actually known as a ferrite choke. And you probably have one around. I know I do. Very, very close to me. And if you're running a computer or a power supply, you probably see one of these. Anyone ever see one of these nearby on their
Oh,
computer
yeah.
power supply?
Yeah, I didn't
Good.
know what it was though.
So you're probably wondering what is in there, right? Okay, so what's in there is, now, typically something that's a ferrite is known as, it contains something known as a ferromagnetic material. So ferromagnetic comes from ferro, which is iron. So iron is one of the really popular ones, but you can also have cobalt and nickel, and there are a bunch of other ones as well. So what you would typically do in this case is you end up having a situation where the different materials that you use, the different metals, you combine them in different proportions, you grind them all up, you mix them with glue, and you bake them into a shape. And that basically creates a good path through materials that respond very well to magnetic fields, which tend to constrain the magnetic fields and then burn up all the energy as heat. Well, if I have energy flowing this way and it suddenly encounters something that looks like, you know, a place where magnetic field energy goes to die because it turns it into heat, what I've basically done is taken all of the energy that flowed as current that generated a magnetic field and taken the magnetic field and shut it down. It said, yeah, okay, it's great that you have a magnetic field. I'm going to use up all that energy right here. So that current never makes it to the other side. So the difference in frequency between voice, which is, let's say, 1,000 hertz, and RF, which is, let's say, 3 megahertz, is very, very different. So what this allows you to do is take the voice and pass it through and take the RF and kill it. It allows you to basically separate the two. And this is known as a ferrite choke. So one thing that is interesting about ferrites, there's a company called Ferrite. And Ferrite's thing. Oh, stop. Basically, Ferrite's thing, the whole thing that Ferrite does is they make RF chokes. Palomar Engineers is another one. Notice they have different mixes. These are just a few of them. And notice they have different frequency ranges, different mixes. Here's manganese and zinc. Some of them are iron. Some different materials basically function in different proportions at different frequencies. So if you know the frequency that you're trying to suppress or build a transformer for, You would basically pick your material and pick the shape and pick the size and either snap a ferrite on or take your cable and wind it around and around and around and around. And by doing that, you would basically give yourself a ferrite choke. Okay. Where should the negative power return of a mobile transceiver be connected in a vehicle? You'd never want to assume that the ground of a vehicle is a good ground. You know, the electrical system, the best place to hook up a ground is right at the battery or to the engine block, because they're connected right to each other. You know, in theory, your entire car, the whole frame of the car acts as a DC ground, but it's not necessarily a very good RF ground. It's also not necessarily designed to handle, 25 amps. If you hook up your radio's ground to, a spot inside the trunk, and everything essentially connects back to the battery, but through a bunch of welds, how good are the welds? They're good enough to hold the car together, but are they good enough to carry a lot of RF and DC current? I don't know. You really don't want to do that. So you just want to connect directly back to the battery.
How about the frame? Same thing?
That's the same thing. Who knows? The most reliable way to do it is to take a big fat piece of cable and hook it directly to the battery. How can you determine the length of time that equipment can be powered from a battery? You have something called an ampere hour rating on every battery. That can be amp hours, which is basically an amp times an hour. So if you have a 1 amp hour battery, you can draw 1 amp for 1 hour. If you have a 100 amp hour battery, you can draw 1 amp for 100 hours. In theory, you can draw 100 amps for 1 hour, but it doesn't really work that way. Okay, operating controls. What's the effect of excessive microphone gain on single sideband transmissions? Essentially, that's the effect of these really loud. Starts to get distorted. So if you have too much gain, it tends to no longer keep the amplifier in a linear mode, and then it starts to have distortion. The result of tuning an FM receiver above or below a signal's frequency, that is distortion of the signal's audio, and I can probably demonstrate this. Let me see if I can do it. Okay.
Lows in the mid-30s.
Can everybody hear this?
South wind 5 to 10 miles an hour.
I'm listening to NOAA weather
Rain
radio.
100%.
Ready? I'm going to tune off frequency.
Rainfall amounts less than a tenth of an inch. Sunday, rain. Highs in the upper 40s. Southwest wind 10 to 15.
So that's what happens if you mistune FM. Okay, distortion of audio. If you're transmitting, everybody will hear you as distorted as well if you're off frequency. Okay, how do you enter a transceiver's operating frequency? You have a keypad or a VFO knob, and I am going to conveniently bring up that ICOM 7300 again, if I can find it. You know what? I'm gonna go to a bigger radio. Let's see if I can bring this up. Yeah, there we go. Nope, wrong one. ICOM 7610. This is the big brother, the one that I can't afford. Okay, so notice what we have here. We have a big frequency knob that's called a VFO, or variable frequency oscillator knob. We also have a keypad in the upper right. The keypad allows you to enter a frequency directly. So let's see, a way to access a favorite frequency or channel on a transceiver. Most transceivers like this will typically have between 500 and 2,000 memory locations these days. So, yeah. So I mean, it's just just a computer, right? So it remembers all of your operating modes, the mode, the filter settings, the frequency, whether or not it was split operation, and you just write it into memory. Some of them actually, because they all interface with computers now, you can actually run software that allows you to program the radio from somewhere else, like from a computer, which is really helpful if you travel from place to place and you have a program that's set up for, let's say, Houston, and a program that's set up for Tucson, because all of your frequencies are going to be different. So before you go there, or when you get there, you basically just dump in the profile for that location, and the radio acts completely differently.
Hey Scott, are you showing the PDF? Because right now I still see the
Yep.
the webpage you had.
Right. Yep. You still see the radio, right?
Yeah.
Yep.
It changed shape, and so I thought you were trying to share the PDF, and my picture hadn't adjusted. But if you're showing the website, that's fine.
Oh no, I'm just showing the website. There. Is that better?
Yeah.
Okay. All right. The scanning function of an FM transceiver. I will stop sharing, by the way. There we go. The scanning function of an FM transceiver allows you to check through a bunch of frequencies very, very quickly. Some radios actually have the sole functionality of being able to scan through a lot of different frequencies, like 100 per second. We would typically call those a scanner. Most handhelds, for instance, like this one that I have, this can do somewhere on the order of 10, 15, 20 channels a second, which is pretty darn fast. But, like a real scanner can do 50 or 100 channels a second. So some people actually have scanners, and they're also able to do things that a typical handheld cannot, such as be able to receive trunked radio systems and digital radio systems and things like that. The purpose of a squelch function. Okay, so what we're going to do is I am going to pull up our web SDR again, and I am going to, while I'm doing that, I'm also going to open up my handheld, and I'm going to make sure that my audio is on. And can everybody hear this? Annoying, right? This is squelch. That's squelch. Squelch basically mutes the receiver output when there's nothing interesting to be heard. So let's say that you've got a weak FM signal. Does everybody hear that? No, because I have the squelch turned up too high. So if somebody's weak, you actually have the reason to take your squelch and turn it off. You're trying to hear something that's weak. Okay, repeater offset. Okay, repeater offset, what we're going to do is for the first time, we're going to draw a repeater. So a repeater has a transmitter and a receiver. And they are right next to each other. And there's something called a controller, which is basically a computer in a box. A computer in a box that takes receiver input and forwards it to the transmitter, but only when necessary. So what happens is now that the receiver is connected to an antenna, and is listening on, let's say, a published frequency, and the transmitter is connected to an antenna. It could be the same antenna or a different antenna. And it is transmitting on a published frequency. Now, the way that this works is that if you look at a repeater, the transmitter frequency will be the one that is the defining feature of the repeater. So this repeater, let's say, operates on 146.72 megahertz. That is its published frequency. If you want to listen and see if the repeater is active, if anyone is using it, you will tune your radio to 146.72 megahertz. But now let me ask this question. What would happen if the repeater receiver operated on the exact same frequency as the transmitter? Your transmitted signal would go out into the world and be picked up by what?
Your receiver.
Okay, that would not work. That is why we don't do that. So what we have to do is we have to have the receiver and the transmitter operating on different frequencies. The difference that we use is known as the offset. And on the 2 meter band, it's 600 kilohertz. And depending on where it is, it's either plus or minus. The dividing point is at 147.00. If it's at 147.00, the offset can be either up or down. If it's below 147, it's minus. And if it's above 147, it's plus. So for this repeater, because its frequency is at 146.72, its offset would be negative, a minus offset. So it would be published as minus 600 kilohertz offset. So that means that in order to be heard by this repeater, you would have to tune your transmitter to transmit on 146.12 megahertz to be heard by the repeater's receiver. And again, that's known as an offset. So the repeater is listening for people to be transmitting on 146.12 and receiving it, sending it through the controller, and putting it out on a different frequency. These could actually be the same antenna. That requires a lot of filtering to do, but it's known as a duplexer, and it's done all the time. So basically, again, this is called an offset. And in this case, it's minus 600 kilohertz. On the 70 centimeter band, it's typically 5 megahertz. So if I had a published frequency of 446.375, well, if I added 5 megahertz, it'd be 451. That's not in the ham band, so it's actually negative. So it would be 441.375. So on the 70 centimeter band, it's a 5 megahertz offset. On the 2 meter band, it's a 600 kilohertz offset. Okay.
Scott,
Yep.
I have a question about those particular frequencies and that chart that we were given. On the exam, is
Yep.
that available, or do we have to memorize those channels, those frequencies?
What, like this? The band plan?
Yes,
You got to memorize them.
you have to memorize it. Okay,
Yep.
so the ones on the right side are the ones that are really important.
Well, basically to know that the 2 meter band goes from 144 to 148. The 6 meter
Okay.
band goes from 50 to 54.
Okay, and
70 centimeters.
the red ones on the right side, those
the-
seem to come up with some of the practice questions.
The only one that you need to know, this is on 146.52, that's the national simplex calling frequency.
Okay.
Notice it says national calling frequency.
Yep.
That is the only one that you really need to know.
Okay.
And the reason that everyone needs to know that is that's kind of like, it's not, I wouldn't say that it's the emergency channel, but anywhere you go in North America, there will be somebody listening. Like on every radio that I have, if I'm scanning, it always scans 146.52.
Okay. Okay. I don't know if this is a appropriate time for that, but it just popped up when you were throwing those numbers around.
I haven't, I haven't heard an inappropriate question from this group the whole time. So,
Okay, thank you so much.
all right. Let's see. Other questions from there. Let's see. So we did repeater offset. What function is performed with a transceiver and a digital mode hotspot? That would be communication using digital voice or data systems via the internet. There is a lot of integration between radio and the internet, especially on, for instance, Arden, which is very, very, very high speed in the 5 gigahertz range. We basically have over radio a duplication of, you know, email and stuff like that that's available to be that's available even when the internet is not down. People actually have set up their stations with telephones, full duplex digital telephones, and have set up like a PBX telephone exchange, which they call the bat phone, which uses a high-speed radio as a backbone link. Because why not? It's a way to experiment. It's a way to combine a technology that's commercial and has been used for quite a number of years using the internet. Hey, you know, if you can replace it with a radio backbone, then you have this new fun redundancy thing. And if it turns out that, you know, you lose internet connectivity for whatever reason, you still actually have a way of getting the message across. So, and that's again known as ARDN, which is the Amateur Radio Emergency Data Network. During good times, actually, they can be bridged to the internet as well. So you can be, you know, somewhere far off the grid and still be able to get email and stuff like that. Okay, a talk group on a digital repeater, as we discussed, something using digital mobile radio. That's a way of splitting a frequency in multiple different time slices. A talk group is a way for groups of users to share a channel without hearing each other. It requires time synchronization, which is no big deal on the part of handheld radios, mobile radios, and it allows Group A to use half of the time on a repeater and Group B to use the other half of the time. And you basically say, I'm a part of Group A. You plug it into your radio and it listens for Group A. Or if you're in Group B, it listens for Group B, and they don't hear each other at all. It's like two completely separate transmitters. A digital mobile radio code plug contains access information for repeaters and talk groups. So I don't know why it's called a code plug, but we have a code plug for Eugene that's been worked on for several years by people who live here who are into digital mobile radio. And they will hand that out to anybody who wants it. And that basically will allow them to link up with all the digital repeaters in the area. Has a specific group of stations selected on a digital voice transceiver. Again, you have a group's ID code. Now, this is a little bit of a tricky thing because they say enable the group's CTCSS tone. CTCSS is something that's a little bit different. It's called Continuous Tone Carrier Squelch System, or private line if you're a Motorola person. So what that does is that it's analog. It allows you to basically have a subaudible tone that's transmitted and squelch your receiver if it's not something that you don't have programmed in. But it's an analog thing, not a digital thing. What is the purpose of the color code used on DMR repeater systems? Color code establishes groups of users. So you can call them A and B. You could also call them the red group and the blue group. So that's a color code. Which of the following has to be transmitted? Has to be programmed into a D-Star digital transceiver before transmitting. Okay, D-Star. Okay, so we covered DMR, digital mobile radio. And there's also something called D-Star, which is it's kind of like VHS and beta, for those of you who remember the video cassette wars. So D-Star is another mode of digital operation, similar to digital mobile radio, but it's a competing technology where there's a lot of digital data that is transmitted with your signal in addition to your voice. So basically you just have to put your call sign into your D-Star transceiver before transmitting. so that it actually will pop up on the other person's screen. Okay, so now what we're going to do is we have a perfect example of multiple bandwidth choices. And I think before we do that, how about a 5-minute break? And then I'll take the time to set this up. All right. See you guys in 5 minutes. All right, everybody ready to go again? Maybe not quite yet, huh? Vernon, can you hear this okay?
Yeah.
Okay, good.
Scott, you mentioned last night there's a contest going on. How has it been going for you?
Well, this is it. And I operate typically very low power. I've been running 5 watts, and I'm up to 40 contacts, virtually all of which are around the Pacific. So a lot of Japanese. I worked New Zealand this morning. Nothing really exotic. I made a contact in Guam last night. But I've kind of been waiting for Europe to open up, and it hasn't happened yet, which is a little bit of a bummer. But there's still 36 hours for that window. So,
How about Australia?
I've heard a few Australians. I haven't worked them yet. I heard Malaysia and I think Indonesia this morning and Thailand last night, but they couldn't hear me. Too much of a pileup. All right, can everybody see this and hear this? Okay, so what we're going to be talking about is appropriate bandwidths. And it used to be when I first started teaching this stuff that I did not have access to this thing called a waterfall display. A waterfall display is what we're looking at now, which is basically a frequency representation over time of a band. And this is just an absolutely wonderful way of being able to visualize what's happening on a frequency band. So what it allows us also to do is see, for instance, all these down here are Morse code signals. We're listening to a software-defined radio in the Netherlands. And we can now see that we're basically listening to about a 3 kilohertz wide swath of space. So this goes from like 7025 up to 7028. And as you can see, there are 1, 2, 3, 4, 5, 6, 7, 8, maybe 9 signals in that space because they're very narrow. And this is what the chaos sounds like if we don't have any filtering. Now, this filter bandwidth is very much appropriate for, let's say, listening to this. If we switch to the other sideband. Because single sideband is about a 3 kilohertz wide signal. This is a very appropriate bandwidth. You can narrow it down a little bit. Still sounds okay. Now what happens if we narrow it down too much? We've eliminated too much of the information and we can't hear anything. We can't discern anything. Similarly, if we pick the wrong sideband, we're basically listening to the audio inverted. Also unintelligible. Similarly, if we pick the wrong frequency by a little bit, it sounds all distorted. Sounds either way too high or way too low. So very important to pick the proper frequency. This helps a lot as far as being able to visualize it. So now what we're going to do is look at another band right here. And notice we have these things that look like little squiggly lines. This is a very narrow bandwidth digital signal. This is what FT8 looks like. And within this one band, there are probably 20 or 30 signals that you can see, those vertical lines. So in the space of being able to put one voice signal, we can put 25, 30, maybe even more digital signals there. Similarly, we can do the same with Morse code. Unfortunately, this also means that we hear all of them, right? What if we don't want to hear all of them? We have this thing called a filter. This is a digital filter. Filters can also be made of crystals that resonate at certain frequencies. And notice what this allows us to do. Allows us to narrow it down and reduce interference from adjacent frequencies. So a good filter for Morse code is about 500 kilohertz or 500 hertz. That's what we're listening to right now. If we tried to listen to voice with this, there's not enough signal there to actually hear anything. So anyway, there we go. That is how filtering works. So an appropriate frequency filter for single sideband is 2400 hertz. That's a little bit narrow, but it works fine. For Morse code, it's 500 hertz. If your signal, as we heard, if you're slightly on the wrong frequency, you basically sound squawky or Donald Ducky or like way too low. There's something called a clarifier or receiver incremental tuning. This allows you to adjust the receive frequency without adjusting your transmit frequency. The other station might be a little bit off, tuned a little bit off frequency. That basically allows you to make them sound better to you without changing how you sound on the other end. A transceiver's push-to-talk input switches the transceiver to transmit when grounded. It's basically a 0-volt signal. When we ground that signal, it switches the transceiver from receive to transmit. And in case anyone didn't notice, the word transceiver is a portmanteau of transmitter and receiver. Somebody created a new word from two. We're also going to come across in the next section, so we're on page 84, a transceiver is a device that combines a receiver and a transmitter. There's another one, which is a portmanteau of transmitter and something else, a device that converts the RF input and output of a transceiver to another band. It converts it. That's called a transverter. So, for instance, a transverter would be used to convert on our frequency chart the 10-meter band up to the 1.25 megahertz band because there's virtually no commercial equipment available for that band. So what you can do is build your own transverter, or you can buy one if you can find one, that will take your signals from one band and locate them on another band. A device that increases the transmitted output from a transceiver is known as an RF power amplifier. So as we discussed yesterday a little bit, does everybody remember this picture of how a transistor works as far as input and output? Everybody remember seeing that kind of?
Yeah.
That you have three different ranges. You have this range and you have this range. So you have 1, 2, and 3. So if I've drawn it well enough, which I have not, so I'm going to redraw it. You have three ranges. This range right here is known as the linear range. If we are running single sideband or CW, if we're running single sideband, we're typically going to want to be operating in the linear range, where a change in the input results in a proportional change in the output. If we're way up here, a small change in the input results in basically no change in the output. Well, that'll lead to something called distortion, and we don't want that. So if you overdrive an amplifier or you're operating it in the wrong place on this curve, it won't work. It'll sound terrible. However, if you are running in FM mode, what is FM? What does FM mean again, everybody?
Frequency modulation.
So does it have anything to do with amplitude? No. So when you're running when you're running FM, you can actually use a much less linear amplifier because the only thing that you're amplifying is a signal that contains a frequency. that is changing. It doesn't really matter if it suddenly gets bigger here and then smaller here, because what's going to happen is that at the receiver side, you're going to go through something called a limiter, which is going to basically just cap the top and bottom off. In which case, all you're left with is the frequency contained inside, and it doesn't really matter if it's clean or not. It doesn't matter if it gets quieter or louder. So most amplifiers, especially for VHF, because they know that a lot of people use FM on VHF, they're going to have a mode switch that will change how the transistor works. They'll change the bias point of the transistor. And when set to FM, if you try to use that for single sideband, it'll sound all distorted. The reason that it's able to do that, though, is because a transmitter that, an amplifier that runs for FM is typically more efficient than a single sideband transmitter. Okay, so my favorite part of the class. Okay, so I want everybody to unmute themselves. That means everybody, if you can. Please unmute yourself. Okay, here we go. On the count of 3, I want you to say your name. 1, 2, 3. Okay, so what did everybody hear? Yeah, okay. So that basically means that our hearing is not selective enough to pick out stuff that's in here. Now, if we could filter it out and we knew, let's say somebody's voice was at a certain particular range, we could actually narrow down our ears so that we could only pick up that range of frequencies. That would be known as selectivity. So we now have another one, which is that, okay, I'm going to whisper, and I want anyone who can hear to tell me what I said. Good morning, everyone. Could anybody pick it up?
I heard you say good morning, everyone.
Okay, but are there people who didn't hear it? Okay, that is the definition of sensitivity. The combination of your receiver, which is, your whatever you're using for whatever you're using for a speaker, whether you're using headphones, whether your ears, whether you've been to a lot of rock concerts in your life and your hearing's not as good as it used to be, like mine, or if you're in a band and you didn't use studio monitors, that would be basically earphones and protect your hearing. So your sensitivity is different. So some their systems were able to allow them to hear me say, good morning, everyone, and some people's did not. That's known as sensitivity. A receiver that's more sensitive can hear quieter things. Okay. Moving on. Okay, so with regard to sensitivity, let us say that we're now talking about a radio frequency signal that's coming down through a piece of cable. And we have a receiver that has a certain amount of sensitivity. A signal that is of a particular amplitude gets to a certain point in our system. So let's have our antenna. And we have it coming down through a cable to our transceiver. All right, so now we're going to talk about decibels. The signal that's coming in compared to 1 milliwatt is minus 120 dBm. So it's 120 decibels smaller than 1 milliwatt, which is really, really small, but not zero. So our receiver has an amazing sensitivity of minus 125 dBm, and this is actually not all that uncommon. Okay, now if we have a cable that has no loss, so it has a loss of 0 dB, and we have a signal of minus 120 right here, by the time it gets down here, it'll be minus 120 dBm. Will the receiver be able to hear it if it has a sensitivity that can go all the way down to minus 125? Yes or no? Yep, we're good. But let's say that this is real world cable and we have loss in the cable of 10 dB. what's the signal strength when it gets down through that cable? Minus 130 dBm. Can we hear the signal anymore? Nope. Okay. So now we're going to do something to try to help ourselves out. We're going to add something called a preamplifier. And we're going to put it right down by the radio. The preamplifier can take any signal that's minus 125 dBm and boost it by 10 dB. But it can only receive down to minus 125 dBm. Does this preamplifier do anything at all in this case? Yes or no?
Yes, it does.
It does not. Because how much of signal? We still had 10 dB of loss. We're still at minus 130, and the preamplifier has to have a signal coming in that is at least minus 125. So basically, by putting it there, we're amplifying nothing by 10 dB. It would help, except that our signal is already weakened. So now what we're going to do is we're going to take this preamplifier, and instead of putting it down there, we're going to put it up here. All the way up here at the antenna. Now, it has a sensitivity of minus 125 dBm and a gain of plus 10 dB. Is there enough signal up there for the amplifier to get to amplify? The answer is yes. And now we've boosted it so that what was minus 120 is now minus 110. And now we have our 10 dB of loss in our cable, because the cable's still the cable, and our signal is back at minus 120. So, can we hear our signal? We get a big check mark. Yes, we can. And that was done exclusively by taking our amplifier and moving it from here to here. Because you can't amplify what you can't hear in the first place. It's a very important rule to remember. You can't amplify what you can't hear. So if you can catch it before it drops down to the point of not being able to be heard and amplify it there, then you can recover it. So that's why you typically will, if you're putting in a preamplifier, you want it as close to the signal source as you can so that you can boost it before it disappears. Okay. Let's see. A device that converts a signal from one frequency to another is known as a mixer. Oddly enough, if everyone remembers that word transverter, at the heart of a transverter is a mixer. The name of a circuit that generates a signal at a specific frequency is an oscillator. So let's say that I have a transistor like this, and I take some of this output signal and I put it into the input, or I take this and stick it into the input. And I don't use anything else. What will happen is that if I manage to trigger this thing on somehow, it will go like this. As soon as this goes on, some of that signal that says that it's on will feed back into here, which 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 will feed back into here. This is known as feedback. And this is actually known as positive feedback. Normally, we don't like positive feedback. Why don't we like positive feedback?
No way to control it.
There's no way to control it. Is that, if anyone has ever heard a PA system where the speaker and the microphone are too close together, what do you get? Right? You get a squealing sound because there's no way to control that. Well, if you select your components correctly and you build the circuit on purpose to oscillate at a particular frequency, then you have something called an oscillator, and you're actually controlling it. But it's the same basic concept of positive feedback, where you're basically using an amplifier to generate a particular frequency. Okay, and let's see, the action of combining speech with an RF signal is known as modulation. And that works for digital, it works for lots of other things. Modulating is basically taking an RF carrier signal and making it carry information. All right, so we are now on page 87 of the PDF.
You're not
Yes.
sharing the PDF.
I'm not, and I will now. Thank you for that. Oh, I like it when everybody reminds me. Thank you for that. All right. We are on page 87 of the PDF. So symptoms, cures, and symptoms, causes, and cures of common transmitter and receiver problems. Okay. So thinking about this, what happens if you stare at the sun? Besides the fact that you might actually hurt your eyesight, can you see anything else if you're staring at the sun? No,
you
because
get swamped.
because your vision is now overwhelmed, right? Now, it is entirely possible that, even though there might be something bright green right next to the sun, you can't see it because your vision is just simply overwhelmed by that, right? Even if you're just staring at a bright light. I don't recommend doing it. A radio basically can work the same way. You basically have a certain amount of available receiving power, if you want to think of it that way. And even if you're not listening for a particular frequency, if there's enough of a signal coming in, it'll overwhelm your ability to hear other stuff. This is actually evidenced by, for those of you who end up with a radio and you hook it up to a big antenna, if the radio does not have very good filtering and you drive into an area where there's a lot of pager systems and like police radios and things like that, public service, there's a lot of RF floating around at different frequencies. It will basically desensitize your radio and you won't be able to hear anything, even though you're tuned to that place. So that's kind of what we're talking about in this case. Which of the following can cause radio frequency interference? Okay, it's fundamental overload. That's basically there's just too much RF floating around. Harmonics. Okay, a harmonic, for those of you who are musicians, if 440 hertz is an A, 880 hertz is a harmonic of that. It's an integer multiple. So is 1320. Now, interestingly, 1320 is no longer an A. I believe it's actually a fifth. A, B, C, D, E, F. So I think it would be an F. No, it'd be an E. It's a perfect fifth. But it's actually a harmonic. It's an integer multiple of the initial frequency. So if I had a transmitter that was on 5 megahertz, my harmonics would appear at 10, 15, 20, 25, 30, 35, 40 megahertz. And as I went up in frequency, they would typically become weaker and weaker. But still, a harmonic, let's say I'm transmitting on 5 megahertz for some reason, there'd be a harmonic on 10 megahertz that if I was trying to listen to another station on 10 megahertz, I might hear that first one too. So that can cause interference. A spurious emission is a signal that is not harmonically related. It's just basically a random signal at a random frequency that for some reason is being put out by a transmitter. What actions should you take if your neighbor tells you that your station's transmissions are being interfered with? The big one is go around your own house and make sure you're not interfering with your own house. If you're not interfering with your own house, then you need to go and, then the problem is at your neighbor's house because you're operating legally. Okay, if you have non-fiber optic cable TV, so basically your old school cable TV cable, those connectors have a way of unscrewing slightly over time. And if they do that, they're no longer creating a closed system. It becomes kind of an open system, and open systems become dirty cable, and that tends to leak. That leaks signals out, that leaks signals in. So If signals leak out, then you can be interfered with. If signals leak in, then your cable TV signal can be damaged. So tighten all the connectors. What can cause a broadcast AM or FM radio to receive an amateur radio transmission unintentionally? All right, so my parents had a stereo in our house, and my transmitting antenna was right outside of the front window. And whenever I was transmitting, they knew I was transmitting because I would come through on the stereo. And they couldn't hear what I was saying, but they knew I was there. And that's because the AM or FM radio can't reject strong signals outside the band. They have the frequencies are far, far apart. But again, just like, looking at the sun, if there's if there's something green right next to it, you'll never see it because you're just unable to. To reduce or eliminate fundamental overload, you can install a filter to block the interfering signal. So, how can fundamental overload be reduced or eliminated? You can block the amateur signal with a filter at the antenna input of the affected receiver. In theory, if I wanted to make sure that my signal did not get into my parents' stereo, I could have taken my parents' stereo and put an RF filter on the input of the stereo. We never went to that point. Now, it used to be that because the telephone systems were owned by the Bell Telephone, if you had a nearby ham, and remember hams are allowed by law because they are licensed to transmit, that was interfering with your telephone line, the phone company would actually come out and put a filter, an RF filter, on your telephone to keep it from being interfered with. That's when they owned the phones. Which of the following can reduce overload of a VHF transceiver by a nearby commercial FM station? Okay, you can install a band reject filter. And I think it's time to talk a little bit about filtering. Okay, so a tuned circuit is made up of capacitors and inductors. We talked about that yesterday because they're frequency-dependent components. So if, for instance, I have a filter that looks like this, at very high frequencies, capacitor will allow things to pass. Low frequencies will get blocked. Well, if any of the low frequencies make it to this point, an inductor is basically a ground. It's basically it's basically a closed circuit for low frequencies. So the low frequencies will go here, and all I will be left with is high frequencies. If I were to draw a frequency response graph for this, I would see that signal strength would be 100% until at some point it dropped off. And that would be called a low pass filter. This can also be done with digital signaling, but we're actually doing components, capacitors and inductors for this case. This is known as a low pass filter. So I could actually take these components and I could move them around. So let's say that I reverse them and I put the inductor up here and a capacitor right here. Well, I meant to draw a high pass. There we go, high pass. Okay. Okay, so now we're going to draw an inductor here. And okay, so in this case, what happens is that high frequencies would get blocked, low frequencies would pass, and high frequencies go down through here, And the only thing that comes out are the low frequencies. So this is known as a low pass filter. So again, if I were to reverse these and do, whoops, that, then these would get reversed, and this would be called a high pass filter. So what if I took these two filters and I cascaded them? If I took, erase all that. If I made this a creative looking filter where I did this, and I took a filter that looked like this, and I followed it with a filter that looked like this. Well, if I pick my components correctly and I select my cutoff points based on those values, I have right here, this section is a low pass, and this section is a high pass. If there is some intersection of these, I basically have this. And this is known as a band pass. Because there's an actual just a single range of frequencies that gets through. And that's known as a band pass filter. If I were to flip that over and combine my components differently, and I had something that looked like this, where only a certain range of frequencies were cut out, this would be known as a notch filter or a band reject filter. And the bandwidth of a filter is actually measured by something known as a 3 dB point. So when the pass band drops down by 3 dB, that's known as the bandwidth of the filter between those 2 points. And that's 3 dB is important because that's known as the half power point for obvious reasons. Because 3 dB is, as we talked about yesterday, how many times? 2 times. Or minus 3 dB is 1/2. So that's known as the half power point. So the 3 dB mark is actually very important in this case. Okay. What should you do if something in a neighbor's home is causing harmful interference to your station? Okay, well, there is now something that we're going to talk about, which is the fact that you have a license, and depending on what it is that's causing harmful interference, they don't. So, this right here, for instance, anybody know what this thing is called?
That looks like a remote control.
That is a remote control. Okay, excellent. So how does a remote control work? It sends out an infrared beam of energy to your TV or to your cable box or whatever it happens to be. It has that little window in the front. Well, it could also send out RF energy at various different frequencies because there's circuitry inside. And there's obviously an oscillator of some kind in here that makes it work in the first place. And any piece of wire can turn into what?
Antenna.
An antenna. So if you have an oscillator, which has frequencies, and a wire, which functions as an antenna, what does this thing turn into? If it has a frequency that's being generated and an antenna built into it inadvertently, what is this thing known as? This is a transmitter. That's right. And in fact, most electronic devices, whether or not they are designed to be transmitters or not, transmit energy. The more devices you have out there, the more RF energy is generated. This is why in our electronic world we have so much radio frequency interference in the world, because we have so many electronic devices out there. I mean, you think about a cell phone. Independent of the fact that this is actually a 4-band transceiver for sending voice and data, there's also a ton of other stuff in here that generates radio frequency energy. You can actually hear this if, for instance, you have a set of headphones or a headset like I do, and you put your cell phone right next to the pickup. You'll occasionally hear doo 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 as the cell phone does various different things and transmits out signals, and they're picked up by my headset. So what happens here is that there is something called, there are different parts of the FCC rules that govern certain things. We're going to cover this one because it's really important. Part 97 is the part of the FCC rules that governs ham radio in the United States. This is what allows us and permits us to become licensed in the first place. And in here, if there's ever a question, is it in the rules? It is in Part 97. If it's not in Part 97, it's not a rule regarding ham radio. This determines like what your transmitter output can look like as far as harmonics and spurious emissions. This determines how wide your signal is allowed to be. This shows what you are allowed to do and what you're not. If there's ever any question, you go back to Part 97. Now, Part 97, again, also defines the whole concept of us being licensed. There's another part, which is Part 90, for instance, which is commercial radios. There's another one, which is Part 95, which is things like CB. But there's another really big one, which is Part 15. Part 15 is basically anything that is not designed to transmit a signal, but does so anyway. By rule, this covers power supplies, it covers, remote controls. It covers a lot of different things. So Part 15 of the FCC rules is basically incidental and unintentional transmitters and receivers. So what if I have a Part 97 amateur radio station transmitting a signal legally into the world, and my neighbor has a television, let's call it a Roku TV, and whenever I transmit, their TV shuts off. And we can establish the fact that it shuts off because there was some signal that got into one of the wires inside their TV, which was connected to something which simulated a signal that said, oh, somebody hit the power button. I am a Part 97 licensed system, right? I am legally operating. This is a Part 15 device. By rule, a Part 15 device cannot cause interference to other licensed services. Amateur radio is a service in the eyes of the FCC. And a Part 15 device must accept interference from any other licensed service. And again, we are a service, which means that we are covered by certain rules that Part 15 is not. So let's say that I am legally operating and I cause my neighbor's TV to turn on and off. Whose fault is it? Who's responsible?
They are.
They are. Now, it is probably in your best interest to not piss your neighbor off if you want to stay neighborly. But ultimately, it is not your fault. It is their fault, and it's their responsibility to fix the problem. So the first thing you want to do is make sure that you're really transmitting legally, right? Make sure that your signals are really nice and clean. Work with your neighbor to identify the device. Try to figure out what's causing interference. If you're interfering with them, you try to figure out why you're interfering with them, and maybe you help them install a filter. If they're interfering with you, then maybe it comes down, and this actually happened to me. I have a neighbor 3/4 of a mile away. This is a good example, and I'm going to spend the time to do this. Okay. Every piece of wire can function as a what, everybody?
Antenna?
Antenna, yes. Okay. So let us say that in my neighbor's home, they have power circuitry. They have power lines running throughout the house from a main breaker panel. Right? Okay. And part of this is that they also have a telephone line, but they only have a telephone line in this one location in the house. And they really want the telephone line up here. So what they do is they connect an intermediate device which uses capacitors and takes a phone signal and goes like this, and they have another one that goes here, and it uses the power line to carry the phone signal. Everybody with me so far? It's a wired system that allows you to use the power lines in your house as to carry phone signals around the house and connect to other points. So I noticed that there seemed to be an FM signal on 3.523 megahertz, and it was FM, and I could hear it clear as day. And most of the time there was nothing there, but sometimes there was a female voice on it. So what we're going to do is take a look at our frequency chart and look at the band plan update, and notice that 3.523 megahertz is right down here in the amateur 80 meter band, isn't it? Okay. This caused me a great deal of consternation because I happen to like operating in that band. So I walked around the neighborhood using a receiver, and I figured out where it was coming from. And it turned out that my wife actually knew the person and called her and said, my husband's going to listen to us, if that's okay. So I actually listened to the conversation. And what was happening was that in order to modulate a phone signal that was put out onto their house wiring to be used by another phone, they had so the company that built it had somehow, for some reason, picked 3.523 megahertz. So it was modulating a signal on 3.523 megahertz with their telephone voice, that it could then be used other places in the house. Okay, you have a signal at 3.523 megahertz and an entire house full of wiring. What does that make?
Base station.
That makes a base station where you're basically you're sending your telephone calls all over the neighborhood. So everybody can listen to you. And I told her, and I let her listen to it. She said, I'm going to go disconnect that now. So she pulled it out of the wall and never used it again. But that's a case of a Part 15 device interfering with a licensed service. And sometimes it can take a while to figure that stuff out. Because, it could be in somebody's house. They may not want to take it out. They may not. You may have to convince them, hey, it really is a problem. Okay. No, go ahead.
You have, it sounds like you have multiple types of antennas around your house. How far away from your house are they situated?
I have several that are like over the house. I've got two HF antennas and one VHF.
And no trouble with your devices in the house.
No, not that I've ever seen. I mean, actually, I find that the more common thing that I get is that, like, somebody will plug in the house, like a new power supply, a new wall wart for charging a cell phone. And it's a switching power supply, and it generates all kinds of RF hash, which I can then hear. Because remember, receivers are very, very, very sensitive, right? If we can receive a signal down to minus 125 or 130 dBm, that's a tenth of a billionth of a watt. It doesn't take a lot of energy to generate a radio signal that's a tenth of a billionth of a watt if it's coming from inside your house. So the most common sources of interference are from actually inside your own home. Okay, what can be a problem if you receive a report that your audio signal through an FM repeater is distorted or unintelligible? If you're off frequency, we listen to what that sounds like. If your batteries are running low, that means that you're not potentially deviating your signal as much as it should be. It could also be drifting off frequency, or you could be in a bad spot. If your signal is particularly weak because you're in a bad location, or you're in an area where you get destructive interference and your signal basically cancels itself out, no one will be able to hear you. RF feedback. If you have RF radio frequency energy coming back into your microphone, your signal will sound unintelligible and distorted and garbled. So basically, you notice that a lot of these problems come back to the same symptom, which is, that you sound distorted or unintelligible. So either you're over modulating, or you have RF feedback getting into the system. And if let's say we have a TechNet and somebody tries it out and they say, well, I have this interference. The answer is, okay, it's one or the other. Which one is it? And then it just comes down to, testing and trying a different microphone, moving to a different spot. What can you do if your FM handheld or mobile transceiver is over deviating? Okay, so deviation, if we're doing sideband, the louder you talk, the bigger your signal gets. So that would be a loud signal, and this would be a quiet signal. FM doesn't work that way. The signal that goes into an FM radio, basically the louder you are, if we're looking at the frequency spectrum, here's the center frequency. The louder you are, the further it will go outward. Typically, you don't want to go more than 5 kilohertz lower and 5 kilohertz above. If you are particularly loud or use very high frequencies, your signal can over deviate and end up stretching out all the way to here, for instance. Well, if the receiving station is only listening for signals in this box, and you just put out the yellow box, what happens to the outside part of your signal?
It's dropped.
It gets dropped off. And there's information in there. So if information is lost, what happens to your signal? There's parts of your voice. Distortion. There's parts of your voice which are not there anymore. Which basically means if you over deviate, you'll get distorted. So one thing to do if you have a radio that has a microphone gain control is to back off on the gain. Most handheld radios don't have that, so the way to back off on the microphone gain is to simply take it and pull it further away from your mouth. Similarly, we have people who are under deviating or have very, how shall we say, delicate voices in our radio club from time to time, and they'll talk like this because they're used to, they're inside. They're talking with their inside voice. And on top of that, they'll hold their radio out here, and you can barely hear them. And the answer is, okay, what I want you to do is use your assertive outside voice like you're on the playground, and I want you to get that radio right up to your mouth. And then the deviation comes up, and the signal's nice and audible again. So that's the fix for that. Okay, let's do that. Okay, moving on. Using basic test instruments and soldering. Okay, so what we're going to do is talk about using test equipment. So this is meters and soldering stations and things like that. So here we go. There are 3 basic things that a multimeter can do. It can measure resistance, it can measure volts, and it can measure current. So we'll use E. So this is in ohms, this is in volts, this is in amps. Those are the 3 basic things that a multimeter typically does. A meter is basically just a way of measuring a value of something. So voltage and resistance These are the most common things that a multimeter will do. Most of them also have an ammeter built in as well. So how do you measure electric potential? Electric potential is a volt, so we use it doing something called a voltmeter. So if I have a circuit that looks like this, and here's a voltage, I would basically take my meter and go like this, and here's my voltmeter, and I would put it in parallel with what I was trying to measure. So there's another thing we can do called resistance. And in order to measure resistance, for instance, what I'm going to do is take this resistor, and I'm going to try to measure how much resistance it is. Well, the way to measure resistance is to put a test voltage across it. Once we put a test voltage across it, it now has a current flowing. And once it has a current flowing, I can, in series with this, put an ammeter that measures the current. So I have a voltage, and I have a current, and by Ohm's law, E equals I times R, R equals E divided by I, and my voltmeter divides those two things, and it gives me a resistance. So there's only one trick here. Let us say that you already have a power supply or a battery in your circuit. You say, okay, I want to measure the resistance of this thing. Well, so this has a battery in it and an ammeter. Does anybody see a problem with that? If we draw a place for the current to go, well, some of it's going to go this way, right? Some of it is going to go this way. What's going to happen to the yellow line that when it goes through your meter? Poof. Potentially it'll destroy the meter. So when you do that, when you measure a resistor, you typically want to break the circuit at some point. Some people actually will completely remove the resistor from the circuit or remove one lead of the resistor from the circuit to test it out so that it's isolated.
And that's how it's set up in series instead of parallel, right?
Yeah.
Is because it's its own circuit.
Yep. It's
Okay.
basically its own diagnostic test device. It has a test voltage and an ammeter built into it, and it just uses those to figure out indirectly what, through Ohm's law, what the resistance must be.
Okay.
Okay, let's see. Okay, let's see. How can you damage a voltmeter? Attempt to measure voltage when using the resistance setting, or you attempt to measure resistance when having a powered circuit. That'll do it. When you're measuring high voltages with a voltmeter, so I like to bring this one up, not to knock Harbor Freight. I love Harbor Freight. Harbor Freight makes some good stuff that's inexpensive and serves a definite purpose. See, and they're getting free advertising. Harbor Freight multimeter. Okay, digital AC. Look at this Harbor Freight multimeter. Let's go to Harbor Freight Tools. 7-function digital multimeter. God, I hate Bing. I don't know why I'm on Bing. All right. Notice it's $7, right? Sometimes you'll even get a coupon that you get one for free. Does anyone have a free Harbor Freight multimeter? I keep one in my bag. They're great to have around for measuring 12 volts. And look, they even measure capacitances and transistor gain and diode checks and all kinds of cool stuff, right? But they cost $7. Now, this also amazingly has a setting that says DC volts 250 volts, AC volts 250 volts. Would I ever measure 250 volts using this meter? Personally, I don't think so. You, in theory, could, but I don't think I would trust it to do that, you know. However, if, for instance, this is what I use for work. Everybody in the field uses these. Notice this Fluke 87 true RMS reading multimeter. Everybody see that? Okay, so this true RMS reading multimeter, RMS again is root mean square. We talked about that yesterday. This is a meter that'll go up to 1,000 volts. And notice that it's on sale for $450. The difference being it's a little more accurate. They're both digital. It's a little more accurate, but at the same time, I would trust myself using this to measure 1,000 volts. Whereas that Harbor Freight meter for $6.99, I would not. And again, this is what we use at work. Okay, so when measuring high voltages, ensure that the meter and the leads are rated for use at the voltages to be measured. How is an ohm meter connected to a component to measure its resistance? You put it in parallel, as we showed. Make sure that the circuit is not powered when taking your measurement. Okay, now another one is because of the fact that an ohm meter has a power supply built into it, it has a battery and a meter. If you happen to find a circuit where when you don't know what's in the circuit exactly, but when you hook up the ohm meter to it, it looks like a short circuit, but then over time it goes to an infinite resistance, which would be an open circuit. That's an indication that there's a capacitor in the circuit. And you're charging the capacitor. And because it's using Ohm's law to indirectly tell you what the resistance was, if the capacitor charges up, once it's charged up, no more current can flow into it because it's full. And if no current flows, then your current is zero. If your current is zero, ergo, you must have an open circuit. So your resistance is infinity. So if you see that your resistance changes from 0 all the way up to infinity in time, you're basically charging a capacitor. Something used to measure electric current, again, is an ammeter, like an amp meter, because current is in amps. When measuring current, an ammeter, unless you're using an inductive clamp meter, which we sometimes do for circuits that we can't break or are carrying very large currents, you would typically have to put it in series. The way that an ammeter works is that the current flow actually goes through a coil. The coil generates a magnetic field, which causes a meter, if it's a mechanical meter, to move. Which of the following types of solder should never be used for radio and electronic applications? That would be acid core. Acid core is used for things like plumbing. So it will destroy a circuit board very quickly. The only kind of solder that you want to use for electronic soldering is this thing called rosin core. And if anybody plays a bowed string instrument, like a violin or a cello or anything, rosin is the exact same thing that you wipe on your bow to make it nice and slippery. So rosin core solder is used for electronic soldering. A cold solder joint is basically something that mechanically might be a decent joint, but if the temperature changes or it gets jostled, it was never really a good electrical joint. A good electrical solder joint is nice and smooth. It actually looks kind of reflective and shiny. A cold solder joint will often look rough and lumpy, and it might electrically be okay until you're out in the field and then suddenly it's not and your thing doesn't work anymore. Okay, operating procedures. How about another 5-minute break, everyone? Does that work?
Yeah.
Okay, 5 minutes. Think of some more good questions.
Hello, is Mike Habner still in the room? Pardon me, that's Matthew Habner. He's still in the room? I'll catch him when he gets back.
All right, everybody ready to go again? Is everybody ready?
Yes.
Okay. All right, we are into operating procedures. This is the 93rd page of the book and the PDF. Most technicians purchase a VHF, UHF, FM transceiver as a first radio. What type of amateur station simultaneously retransmits the signal of another amateur station on a different channel or channels? That would be known as a repeater. Repeater is a station that functions in automatic control mode. Essentially, it repeats everything that it hears, independent of what that thing happens to be. If that's somebody transmitting something that contains content that is inappropriate, well, it's still going to retransmit it because it's automatic. Things that retransmit automatically are repeater, auxiliary, or space stations. A space station, by definition, is anything that is 50 kilometers above the Earth's surface or higher. An auxiliary station is kind of like a forwarding station that would be used to link two different repeaters together. So that could be something on a ham radio microwave frequency, for instance, where it basically takes a signal and just receives it and forwards it to somewhere else.
Who maintains the repeaters?
Whoever owns the equipment and is responsible for it.
Well,
That could be an individual, that could be a club. And repeaters themselves, you figure, okay, well, there are obviously different frequencies that people need to use in order to run a repeater. So every area has an organization known as a frequency coordinator that's responsible for making sure that people who want repeaters can get them, can get frequencies to use them on. And if there happens to be like a dispute, multiple different stations want to use a given frequency, they can figure out how to do that. It's a very thankless job. A linked repeater network is a system by which multiple repeaters on different frequencies are linked together, where any received signal received on any of the repeaters is retransmitted by all of them. The benefit of such a thing, for instance, is in like Oregon, we have a system known as the Peak Radio Association, where we have 50 odd repeaters that are all linked together. Around the state, they go into Idaho, they go into California, Nevada, up into Washington. If anybody can use any of them, they can use all of them, which means that two people on little handheld radios, 250 miles apart, can have a conversation over this system. Now, it ties up a lot of repeaters, but at the same time, anybody else who happens to be able to hear any of them can also join the conversation. It's also very helpful for getting emergency assistance out, or if there happens to be, let's say, a storm or something like wildfires, which we've had, those repeater systems can be very, very useful. Again, that's called a linked repeater network. Does anybody remember what the typical frequency offset is in the 2-meter band? It's right there, plus or minus 600 kilohertz. And in the 70 centimeter band, plus or minus 5 megahertz. This is just something that you have to memorize. Okay, CTCSS. This is also known as private line or subaudible tone. So the repeater that we have here, I'm going to bring up two different ones. We have 146.72 megahertz with a minus 600 offset, minus 600 kilohertz, with a subaudible tone of 100.0 hertz. We have another one that's 145.45 with a minus 600 kilohertz offset and a tone of 123.0 hertz. So these tones are known as CTCSS, and they were created by Motorola a long time ago. There are typically 38 available different tones. Motorola called them private line or PL, and the reason they came about was because analog repeaters exist on a certain number of different frequencies. Well, if you get into 2 meters, you'll notice that that number of frequencies is actually limited, right? Because they have to be spaced out a certain distance to keep from interfering with each other on the spectrum. Well, what happened was, if you look at the Los Angeles basin, which has a lot of people and a lot of hams, you will find that in order to put up all these different towers around the basin, that there are a lot of transmitters and there is a lot of need to share frequencies. Well, let's say that you have this one, which is on 146.72, and this one, which is also on 146.72. And somebody who is down here in the LA basin, if they transmit into a repeater on one of those frequencies, will bring up this one and bring up this one. And what do we know about FM? If we have two signals of equal strength being received, who wins?
Neither.
Neither. That's right. So clearly there had to be some way to eliminate this problem. So Motorola came up with this thing called PL, which is private line, which is a subaudible tone which is stripped out of the transmitted audio after it's received by the repeater. These range from 67 to, I believe, 253 hertz. And there are 38 different ones that are generated by a radio, and essentially if you don't have the right PL tone, the receiver will not listen to you. If you do have the right PL tone, let's say this one is set up for 100.0 hertz, and you're transmitting at 100.0 hertz PL, you will activate only this repeater. This repeater, if it's listening to 156.7, you will not activate this repeater, thus eliminating the problem for the most part. And again, that's known as CTCSS, Continuous Tone Carrier Squelch System. Now there's another type of tone called DCS, which is Digital Code Squelch. And this is this is actually a digital squelch. It's actually a digital code by which the frequency on which a radio is operating and transmitting varies very slightly up and down based on a particular code. So if the receiver picks up that code, those slight changes in frequency over time, it'll say, oh, this is meant for me. And if it's not there, it won't receive it and it won't retransmit it. So if you have the improper offset set, or you have the wrong tone, or you have the wrong DCS code, the repeater will not retransmit your signal. Okay, reverse function. So let's say that, again, our repeater transmits on 146.72 megahertz. That is its published frequency. Well, in order to get into this repeater, I have to be transmitting on 146.12. And let's say that there's another station over here that is transmitting on 146.12, but for some reason they can't get into the repeater, but I think they're nearby. I can actually set my radio to reverse so that I can actually listen on the input frequency. That's known as reverse split. Allows me to listen on the input frequency instead of the output frequency. What could cause your FM transmission to be distorted on voice peaks? This is basically the same thing as pull that microphone away from your face. You're talking too loudly. The appropriate way to call another station on a repeater if you know the other station's call sign. Okay, let's see if he's here. KI6 LNB, KI6 LNB. This is N7JI, over.
N7JI, this is KI6LNB, go ahead.
All right, hi Larry, good morning, and thanks for being here this morning, over.
Thank you. I'm very glad to spend the time with you to learn all this coagulation of ham information that I have running around in my head.
All right, very good. Well, I'm going to get back to teaching. Thanks again. KI6LNB. This is N7JI. 7-3.
7-3 to you. This is KI6LNB, clear.
Okay, so what we just did is we just had a contact. So the way to call another station, you say their call sign, and then you say your own call sign. If you just want to say that you're here, you can just say, this is N7JI. If you want to say that you're listening or waiting for a contact or something, you're looking for anyone, N7JI listening, N7JI monitoring. What describes an amateur station that transmits and receives on the same frequency? That's known as simplex. For the most part, if you think about your telephone, how you can hear yourself and the other person at the same time, that is known as duplex. In particular, on the telephone, that's known as full duplex. Typically, we don't do full duplex anyway. We do half duplex, 2 different frequencies. But if you're on the same frequency, that's known as simplex. Why are simplex channels designated in the band plan? The band plan is set up so that it optimizes use of frequencies, optimizes availability of repeater channels. So basically, if you're 600 feet away from somebody else, you can pick a simplex frequency and talk to each other. And if nobody else outside of the area is really needed to be hearing you, you just operate simplex back and forth and you don't tie up a repeater. The national simplex calling frequency on 2 meters is 146.52 megahertz. This is something that you need to commit to memory because anywhere you go in North America, if you're on 146.52, if there are hams around and they're on 2 meters, they are probably listening there. The much less frequently used, but still significant calling frequency for 70 centimeters is 446. Okay, so now we're into HF operation. Hey, everybody, what are the frequency limits for HF, high frequency, in megahertz?
3 to 30.
Correct. How about VHF?
30 to 300.
And UHF?
300 to 3000.
Very good. Like I said, one of those is guaranteed to be on your exam. Okay, what is the meaning of the procedural signal CQ? CQ means I seek you. I'm looking for anybody. Before calling CQ, first of all, you have to make sure that your frequency privileges allow you to be there, right? If your frequency privileges, because of your license class, don't allow you to be there, you shouldn't be transmitting there anyway. Once you've established that, you listen on the frequency and make sure you don't hear anyone. And then finally, you ask if the frequency is in use, because unlike a lot of other different things, just because you can't hear somebody doesn't mean that they're not there. So we're going to draw a triangle with A, B, and C, the 3 different stations, and you are station A. Station B and C are in a long back and forth conversation with each other. And you don't really know where stations B and C are. It doesn't really matter. But they're in a long back and forth conversation with each other, and each of them is basically talking for 5 or 6 minutes at a time, which is fine. They're allowed to do that. And so station C, when you turn on a certain frequency, has been going for 3 solid minutes, but obviously is not done yet. Well, the interesting thing about high frequency propagation is that you may hear one side of the conversation, but not be able to hear the other side of the conversation. So the 3 minutes that you've been sitting there listening and making sure that frequency is open, you have not heard anyone. The reason you haven't heard anyone is because station B has been busy listening to station C the whole time. And if you say, is the frequency in use? And in Morse code, you'd say QRL. You would get a response, yes, the frequency is in use. But you never would have even known that unless you bothered to ask, because you could not hear station C directly. And that's why it's important to ask, is the frequency in use? Okay, once you've established all this, how do you respond to a station calling CQ? Okay, CQ, 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 N7JI, N7JI, listening. Larry, you're on.
I'm mostly a UHF, VHF person, so I may not get the HF
Well, I'm going to call CQ again. CQ, November 7, Juliet, India, contest.
November 7, Juliet, India. This is KI6LNB. Go ahead.
Okay, there you go. KI6LNB. Transmit. Okay, how do you respond to a station? You transmit the other station's call sign because you're telling them that you heard them, that you're responding to them, and then give your own. And that's it.
Okay.
That's it. Okay, so which of the following is required when making on-the-air test transmissions? You have to identify your transmission. You have to identify the transmitting station, period. And the rules say that you have to transmit your ID, your station identification, which is your call sign, every 10 minutes and at the end of communications. The rules do not say that you have to do it at the beginning, but most of us do anyway. But legally, you have to do it every 10 minutes and at the end. Okay, so you're allowed to operate Morse code. If you take a look at the frequency chart, you will see that one of the things that you can do as a technician class operator, so notice this novice technician voice, and up here there's CW ready data. You'll notice that whenever there is a star, or a little splat looking thing, it says novice and technician. Right up here on 10 meters, you have the entire lower end of the band for Morse code, and you have 200 kilohertz of voice. On the 15-meter band, look at this. You've got lots and lots and lots of space to do Morse code. On the 40-meter band, you've got lots and lots of space to do Morse code. On the 80-meter band, you've got lots and lots of space to do Morse code. So you want to learn Morse code? This comes from the olden days when you got a novice license. That is the only thing you could do. That's how I learned Morse code. That's why I know Morse code, because that was the only thing I could do until I upgraded. But that is still there. So if you get a technician license, you're allowed to do it and practice it and have fun with it. Oh, but because of that, we have to do a couple of Q signals that are involved in Morse code. There's only 2 that you have to know, although there are actually dozens and dozens. The more you operate, the more you know. QRM, sometimes people will actually say this on voice too. QRM is interference from other stations. QRN is natural. So the way to remember this is M is man-made noise and N is natural noise. Natural noise is like static crashes from thunderstorms. QSY. QSY means I'm changing my frequency. Now the nice thing about a Q signal is that if you put a question mark after it, it turns into a question. So say QSY question mark, that means would you like to change frequencies? And then you say QSY, that means I am changing frequencies. Okay, what is a band plan? Beyond the privileges established by the FCC. So it should be noted that the FCC, for the most part, does not tell us what to do with these frequencies. They just say, these are the modes you can operate, and these are your band edges. You're allowed to operate within these bands. There are a couple of places where they say you can only do Morse code or you can only do digital, but for the most part, they don't tell us what to do with our frequencies. A band plan is a voluntary guideline for making sure that we don't interfere with each other. So the reason that we have FM on FM simplex in certain places is because of a band plan. It doesn't mean you have to do that there, but in order to keep the peace, everybody basically agrees that this is going to be used for this. That is a band plan. Which of the following applies when 2 stations transmitting on the same frequency interfere? Well, who owns a frequency? Nobody owns a frequency, which means that you figure it out. And let's say that one station's been operating a net there every day on that exact same frequency for the last 40 years, every single day. You're having a conversation and somebody says, hey, our net's about to start up in 5 minutes. Would you guys move 5 kilohertz? The answer is, well, we don't have to. The other answer is, sure, go ahead. We'll move. So it's really up to you. The amateur radio emergency service. We're into public service and emergency comms. The amateur radio emergency service, which is ARES, and there's something called RACES. Notice they both have amateur and radio and emergency and service. The one difference being civil. Okay, so if it's civil, that means that it has to do with the government. So the amateur radio emergency service and RACES are very, very similar in that they both involve ham radio and frequencies and people and equipment. The only difference is that if it's civil or RACES, it has that letter C in it, is that it involves signing up with a civil defense organization or emergency management in government to be available in emergencies. If you're in ARES, that's basically a volunteer group that does not necessarily do anything that is involved with the government. It's public service, but not necessarily involved with the government or civil service agencies. That is the only difference. So what is RACES? An FCC Part 97 amateur radio service. Notice that because it's governmental, RACES is listed as Part 97. It's in the rules for civil defense communications during national emergencies. So RACES is basically a more official version of ARES because it involves governmental organizations, and you have to register with governmental organizations to be part of RACES. Okay, when running a net is short for a network. So a network is a group of people who have established a structure or hierarchy of communicating information between different points. So this could be like a daily net where you just get together and talk about lunch. It could be a daily net or it could be a weekly net like we have here in Eugene, where it talks about various different technical questions. We also have a beginner's net every week in Eugene for people who want to get used to operation. There's also a hospital net. Every week, all the hospitals in the state of Oregon get on the air and they make sure that their ham radio stations are working properly. There's nothing else exchanged, just to verify that their stuff is working right. So net control is the station who is basically in the center of the whole thing. So net control basically will say, okay, the net is beginning and the net is ending, and all communications during the net operation have to go through me because I'm the net control. I take check-ins. If somebody wants to talk, they ask me if they can talk. If somebody has information and they want to pass it from one station to another, it can either go through me or they can do it directly if they can hear each other. But basically, the net control station is the traffic cop. Standard practice when you're operating in a net, unless you're reporting an emergency, transmit only when directed by net control. The net control station might say, does anybody have any traffic? Does anyone have any comments for the good of the order? So unless there's an emergency, you wait to be asked if there's any information for you to send across the net. Traffic is literally a piece of information or a message exchanged from one net station to another net station. So traffic might be a piece of traffic. Okay, this is N7JI with traffic for KI6LNB through net control, where Larry, I'm going to go to have lunch at the pizza place at noon. That's my traffic. Over.
I understand that pepperoni is very good this time of year.
Yeah, thank you. And yeah, it is pepperoni season. The harvest has just ended.
Heck, I have a multicolored pepperoni tree in my front yard, so I hope you enjoy your pepperoni in Eugene.
All right, thank you. So that's my traffic. N7JI, back to net.
KI6LNB clear.
All right, so notice we also said back to net. So we basically had permission from whoever was net control to pass our traffic back and forth. So our traffic is formal information going from place to place. So we also do emergency communications drills here in Eugene with the City Emergency Operations Center, where we have people who are part of neighborhood groups using something called CERT, and there will be practice emergencies that are set up around town, and they'll walk around and look for messages in boxes in different neighborhoods, and they will transmit that information across family radio service or GMRS to a local ham. The local ham will pass it to the net. That ham will pass it to the City Emergency Operations Center, and the goal is to see how good we are at, using different frequencies and different technologies, and basically playing a game of telephone. We have the original message. Let's take a look and see what the message looked like when it got there, and see if it was still accurate. So, passing messages exactly as received is very important. Basically looking to see whether or not, let's see, we had a name, and it was kind of a strange name, and we need to make sure that we don't misspell the name, because if the name is misspelled, it might not be the person we think it is anymore. So in that case, we get to use phonetics. So Gary, is your last name pronounced Gurhos?
Gorhus, like gorgeous.
Gorgeous. Okay. Okay, so if I see that and I'm not sure how to pronounce it, and somebody else wouldn't either, and I'm trying to pass that across the net, I would say first name is Gary, Golf Alpha Romeo Yankee. Last name, Golf Oscar Romeo Hotel Uniform India Sierra. So even if I don't know how to pronounce it, or even if the other person doesn't know how to spell it, it doesn't matter. We're using phonetics to get the information across. So use a standard phonetic alphabet. The most common phonetic alphabet to use is the International Telecommunications Union, or ITU standard alphabet. Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, and so on. The preamble of a formal traffic message is all the information at the beginning needed to track it, where it came from, the time it was initiated, where it's supposed to go. What is meant by the check in a radiogram header? Radiogram is basically a formal piece of message traffic that's going across nets. The big thing in there is a check. The check is the number of words or word equivalents in the text portion. So if the message is, I am going to the pizza place. I am going to the pizza place. The check would be 7. If somebody received that message and they said, check is 7, and they only got 6 words, they'd say, okay, well, I obviously missed something there. Let's do it again. That's a very easy way of essentially doing like a parity check on a digital message, except that this is in voice. When do the FCC rules not apply to the operation of an amateur station? And the answer is the FCC rules always apply. However, when are you allowed to operate outside the frequency privileges of your license class, or even outside of the ham bands? And that is in situations involving the immediate safety of human life or protection of property. So therein lies the conundrum that basically you're not allowed to operate outside the ham bands unless it's an emergency. And since the rules say if it's an emergency you're allowed to operate outside the ham bands, you're still operating within the rules, which means that the rules always apply. And the rules basically say if something really bad happens, you can violate the rules and you're still in the rules. Okay, amateur satellites. So time for me to get my brag in. During field day last year, I had my handheld radio and a handheld antenna, and I talked to an astronaut on the International Space Station. One of the highlights of my life.
I talked to a guy who's, sorry, I'm just going to interject with another little story. I talked to a guy whose kid before going to school in the morning, actually talked to the commander of the space station, then went to school and said, "Hey, I talked to the commander of the space station this morning on the radio, and they kicked him out of class for lying." And his dad had to send a note and sort it all out.
Look, yeah, he really did. I did too. It was amazing. And it only lasted about 5 seconds, but it happened. I have a card. I have a card with proof that it really did
Very
happen.
cool.
Yeah, 5 watts and a 3-element antenna pointed up as it was making its pass.
What did you say to them?
I said, well, I heard him calling, and I said, this is N7JI 1 Alpha Oregon. And they said, N7JI 1 Alpha DX, have a good field day. It was what was his name? Shell Lindstrom? Captain of the ISS. Most of the, and the call sign up there is NA1SS. So, NA1 Space Station. Okay, what amateurs can contact the ISS on VHF bands? That would be any amateur holding a technician license class or higher. UV, that would be UHF up and VHF down. So if we look at UHF, that's 300 to 3,000 megahertz, which would be the 70 centimeter band, would be the uplink. And VHF, the most common one, is the 2-meter band. So that would be 146 megahertz. So 440 up and 146 megahertz down. That would be mode UV. It's basically uplink, downlink. Modes of transmission that are commonly used by amateur radio satellites. It's not all FM. There are single sideband satellites. There are Morse code satellites. There are data satellites. Sometimes you'll actually get from the space station, they'll run a special event where they're transmitting photos that they've taken from up there. And they're transmitting them using slow scan TV over the ham bands, which is very cool. You can receive it using a handheld radio as it's flying overhead with a photo decoder. An
I'm going to
SSTV
jump in for a
decoder.
quick second.
Yeah.
The college group that I'm part of, one of our old alumni got to do that for the Sputnik anniversary, and so we have the picture in our group Discord, so we can
Isn't
all
that
see
cool?
it.
And where are you in school?
Kettering, so we're in Michigan.
Okay, cool. Yeah, it's pretty cool when you start realizing, you know what? I'm using a handheld radio, and I'm actually able to decode a photo that's being sent digitally from 220 miles above the surface of the Earth. Let's see. What's the impact of using too much power on a satellite uplink? And essentially, just like if you're screaming, nobody else can hear you. Nobody else can hear anybody else. I guess I should say no one else can hear anyone else. If you're using too much power on an uplink, you'll block access from everybody else. To verify if your satellite uplink power is about right, every satellite transmits an identification beacon. The simplest thing it can do is give its Morse code ID. It can also give digital data saying that its temperature on board, battery charge, computer systems are all okay, etc., etc. So if your signal coming down is about the same loudness, same volume as the beacon, then you're transmitting at about the right power.
It took me a minute to understand what the relationship between the two was. And then it was explained to me that the satellite matches your power. So it matches the power of the receive station.
Mm-hmm.
I didn't understand how the link was between the downlink and the beacon.
Well,
talking about your power.
Right. Well, I mean, basically, the power that you transmit with can turn into, it can turn into the amplitude of your signal being retransmitted. And if you're basically overwhelming the receiver, then yeah, you'll basically have, it will sort of like automatically correct for the strength of your signal. So it's sort of telling you, yeah, you've got too much power. Crank it down, or we can barely hear you. Crank it up. Okay, a LEO satellite. LEO is low Earth orbit. the International Space Station is an LEO or LEO satellite. So is ORSAT-1. So Danae, do you know what the altitude of the ORSAT satellites is?
I don't know it off the top of my head. I should though.
Do you know what the orbital period is?
No.
Okay. Well, the ISS makes one pass about every 92 minutes or so. Makes one complete circle every 92 minutes. So the higher up it is, the longer the orbit, the longer the period is. Okay, a satellite beacon is a transmission from a satellite that has status information in it. Telemetry, what telemetry information is typically transmitted? Health and status of the satellite. That's saying battery voltage, onboard temperature, whether or not the computers are working right, things like that. And because it's only a downlink, you do not need a license to receive anything. Anybody can receive telemetry from a space station. And again, a space station is anything 50 kilometers up or higher. Satellite tracking programs, which of the following are provided? Well, there's a lot of them actually. And one thing I'm going to show you right now is something called AMSAT ISS Tracker. While that's coming up. Okay, so here's very simply. AMSAT is the Amateur Satellite Corporation. They fund satellites for amateur radio. They actually arrange for launch platforms and times for satellites to go up, as well as frequencies. And notice these are all the satellites that are up there. Let's see if ORSAT is listed. Yep, there's ORSAT 0. In fact, there is the ORSAT 0 flight pattern. And let's see if I can get any past prediction for that. ORSAT. Oh, look at that. I got to tell them where I am. CN84 LA. And come on. There we go. Here are the next 10 passes for ORSAT. Isn't that cool? So basically, it's using orbital parameters for the satellite, and it's predicting when and where it's going to be. So you're looking for like a high elevation pass. Ooh, look at that one. 79 degrees, and the duration is over 11 minutes. Now, that's from horizon to horizon. Notice that it's acquisition of signal, azimuth, that's almost due south, and it's going to be exiting almost due north. So it's going to traverse the sky almost from due south to due north. And that is on the 28th at 0114. So that is about 5:15 in the afternoon in Oregon. So if you happen to want to try to communicate through ORSAT, I know you can't right now, but that's what you would do. You would look up and see when it's going to make a pass and communicate and point your satellite and point your radio, point your antenna, and have at it. Okay, things that are required to track a satellite. You have Keplerian elements named for Johannes Kepler. This is basically orbital mechanics. You say where, you basically give it a start and end point and height and things like that. And it will figure out where it's going to be and when, and give you a map and show you when to make your attempt to communicate through it. Doppler shift. Okay, Doppler shift is most often heard when we're listening to a fire truck go by. As it gets closer, at speed, the waves are compressed, making it sound higher. As it's going away, the waves are stretched out, making it sound lower. This actually works on radio too, believe it or not, especially because in this particular case, the thing that's making the radio signals is a satellite, and it's moving at 17,000 miles an hour, which is not that fast compared to light, but it's fast enough that it's actually compressing the waves. If it was transmitting a color, we would actually see a slight shift in the color So if it's transmitting a radio wave, we see a slight shift in the frequency of the radio wave also. So what we have to do is we actually have to account for Doppler shift. So if you're trying to work through, let's say, the International Space Station, you actually have to change your receive and transmit frequencies as it's making its pass, approach, overhead, and going away. So I actually have programmed in 5 different pairs of frequencies in my handheld radio and in my car, in the radio in my car, so that I can actually talk through the ISS as it's approaching overhead and moving away. Spin fade. Okay, the satellites, most satellites rotate as they are in space. So that means that occasionally the antennas will go behind the satellite from you. When they go behind the satellite, they will typically tend to fade out. So that's known as spin fading. Okay, there are many different ways to have fun with amateur radio. Contesting is one. An operating activity that involves contacting as many stations as possible during a period of time is known as a contest. That's contesting. When you're making a contest contact, there is a defined piece of information that is specific to that contest that you would exchange. So in my case, I was just operating the CQ Worldwide. The exchange is your signal report. Everybody is 599. And the zone that you're in. I'm in zone 3. So my exchange for anyone who I talk to is 5993. Similarly, people, after we exchange call signs, will say N7JI 59925. That would be from Japan. And it would go in my log as a verification that I actually made a contact with that station. So send only the minimum information needed for proper identification and the specific contest exchange. Okay, I don't know if anybody noticed there, but when I was on the AMSAT website, it asks for a grid. A grid locator is a letter number designator assigned to a geographic location. So one of the things that I sent out, I believe, to everybody was a grid locator map. Let me see. Grid square map. Yes, I did. Okay. One of the things that I sent out in the packet was this thing called a grid square map. So if we look at, for instance, I'm going to zoom in on CN84. This whole 10 by 20 degree rectangle is CN. The next one over is DN. The next one over is EN. Everybody get the idea here? Then above it, north, it would be FN, or sorry, EO. Below it would be EM, EL, and so on and so forth. So those are the big rectangles, and then each of those rectangles is broken up into 100 different little rectangles. So what that allows us to do is more closely identify where somebody is in a particular place. So this is 2 degrees longitude by 1 degree latitude. So I am in CN 84, and where is Kettering in Michigan?
We're in Flint.
On the hand, so it's down like by the Detroit metro area.
Probably closer to the border between 83 and 82, honestly.
Okay, so it's either EN 82 or EN 83. Now, notice that the UP is up around EN 56, EN 66, EN 76. That might not seem that significant unless you're operating in a mode which has a very narrow beam width, let's say 1296 megahertz, and you're in the Chicago area. If you're looking to work into Flint, that eastern Michigan area, you're pointed almost due east. If you're looking to work into the Upper Peninsula, it's still Michigan, but now you're pointed due north. So knowing what your grid square is actually very important, or it can be very important. A method of locating sources of noise interference or jamming would be radio direction finding. We also have a lot of fun with this. It's called fox hunting, where you take a transmitter and you have it beacon out a signal every so often and you go hide it in the woods. There are actually competitions. There are actually fox hunting competitions where people consider it an athletic event. They carry a radio and an antenna and they run through the woods looking for the transmitters. First person to have them all wins the race. IRLP is the Internet Radio Linking Project. Like I said, there's a lot of integration because there are a lot of people who are very technologically savvy in ham radio. There's a lot of integration between the internet and ham radio. If the internet's available, we might as well use it. So we use something called VoIP, which is Voice over Internet Protocol. Voice over Internet Protocol is a method of delivering voice communications over the internet using digital techniques. We are talking over VoIP right now. That is, even though I sound analog, my voice is being, and my picture are being converted to digital signals, which are being sent over the internet and then being converted back to analog for you to see and hear. Echolink. Echolink is a system by which you can take a phone or a computer or any other device that's connected to the internet, and if you have for instance, a repeater that is tied in to the internet through Echolink, it basically allows you to send in your proof of license to the Echolink people so that you can bring up the Echolink app on your phone, which looks like this. So here's Echolink. It allows you to select, I know it's a little hard to see, but here's Echolink. It gives you a list of stations, repeaters, links, conferences, etc., etc. Allows you to pick one. You can pick a repeater that is active on Echolink, and you can be in Mexico or Uruguay or Europe and use Echolink to use the internet to talk back over your home repeater or any other repeater for that matter. And we have nets on our local repeater here in Eugene. Our repeater is connected over Echolink. And what it allows us to do is, as our members travel to to other places, I travel a lot for work. We have people who go on vacation. I've worked in South America and Europe. What it's allowed me to do is if I have a Wi-Fi connection and I have my phone, I can actually use my local repeater and talk to the people at home and participate in local nets back home. I can also use it to talk to my family because my family, they all have their ham licenses. So if they hop on the repeater, I can make a call over the repeater and they can be in a car somewhere and talk over the repeater with me in another country. So, and that's known as Echolink. IRLP is Internet Radio Linking Protocol. And IRLP is a way of basically connecting a radio to the internet. So Internet Radio Linking Protocol. And you also notice that when you get a handheld radio, you also have this number pad. Everybody has a number pad. Most people use it to punch in frequencies. What a lot of people don't realize is that if you hold down the push to talk button and you push the numbers, you actually have a touch tone pad, just like you do on a telephone, which allows you to punch in touch tones, which a certain code will allow you to access certain functionality, like connecting that repeater to the internet that you happen to be talking on. In which case, if there's another repeater somewhere and you connect it to the internet, you can actually use the internet to pop up on yet another repeater and link repeaters together over the internet. We actually do this here in Oregon. We have, again, the Peak radio system. It's connected over IRLP, and occasionally somebody will bring up a link between this repeater system and another system in England. And we'll have a bunch of people in Western Oregon talking to a bunch of people in England over their handheld radios. Okay, what type of signaling uses a pair of audio tones? DTMF is dual tone multi-frequency, literally two different audio tones. An amateur radio station that connects another amateur station to the internet is known as a gateway. We use them all the time. And now we are on to rules and regulations. And this is the kind of meat and potatoes stuff that we have to do. And you know what? I think it's time to take another 5-minute break. If that's okay with everybody.
Yeah, Scott.
Yes.
This is Steve, I just have a question, real broad question. I've heard some people express some reservations about 5G. What's your take?
It's just another technology.
Good. Okay.
There's a lot of people who are afraid of a lot of things.
Okay.
For reasons that are largely unfounded, you know? I mean, you know, if you actually do the site survey analysis, you know, the RF exposure analysis, unless you're right on top of an antenna, there's really very, very little danger. Most of them are at pretty high altitude. The most dangerous thing you have as far as cell phones go is the fact that you're carrying a cell phone in your pocket.
Yeah.
You know, I mean, this is a frequently transmitting thing. And I mean, it basically sends out information all the time, right? Indicating to the cell system, yes, I'm here. And it adjusts its power automatically to make sure that everybody knows that it's there. So, you know, this actually having a cell phone is far more dangerous than 5G will ever be. And to my knowledge, most people don't die of having a cell phone. So there's, you know, it's much ado about nothing, I think.
Okay.
Just my personal opinion, with a little bit of scientific background behind it.
How does AMSAT get these predictions for ORSAT 0?
Does somebody know? If we, my assumption is that at some point, all the orbital elements were given to AMSAT, and you know, it had to be coordinated. I mean, ORSAT 0 has it has a spot up in space that was allocated to it. You know, you can't just launch something up into space and you know, assume that it's not going to crash into something, I guess. It's got to be coordinated. You know, there's a lot of space in space, but it's not infinite. And you know, I'm going to ask Andrew and see what he has to say, because more than likely they gave them the orbital elements for the satellite, and that's how they know. Thinking that anybody might want to, you know, see it, and here's how you see it. And besides the fact that at some point, you know, like the one that's going up, which is the giant selfie stick, you're going to have to be able to track it. You're going to need to know where it is, because to go from one horizon to the other, you know, that's basically 10 minutes. The thing is screaming across the sky. And the thing is that it doesn't always pass over the same place. You know, the orbit stays constant, but the Earth is turning underneath it. So if you look at what the orbit looks like on a static map of the Earth, it looks like, you know, this, and it always moves around from orbit to orbit, which is why, like, if you look at the ISS, you basically get roughly 7 hours of passes that are usable, and then you're not underneath the orbit for like another 17 hours or so. So, you know, ORSAT is virtually all of the LEO satellites are going to behave in that same way. Maybe it's 7 passes. It might be 7 consecutive passes, but then once those are over, you don't see it again for another half a day, and it changes from day to day. So it's like what is it, like 11 hours? And then like another 12 or 13 when you don't see it. So that time that it passes shifts from day to day. It's not repeated. So you might have evening passes one day, and then a week later you'll have morning passes. Anyway, orbital mechanics. And I'm going to ask Andrew. I'm going to send him a note.
Yeah, I'm really interested to learn more about that too.
Okay.
Especially on like how they can confirm the location, even if they have like the, I don't know.
I know. Yeah, it's actually pretty complicated, but let me see. I gotta find what. Let's see. Sorry, this will take a second. Heck, it's Sunday morning. You can make a phone. So are you guys at PSU on a semester or trimester system?
We're on semesters.
Semesters. Okay. Interesting, because Oregon and Oregon State are both on the trimesters or quarters.
Oh, wait, yeah, it is quarters,
It's
sorry.
quarters, okay. So that means you've got your when does it start? Is it like end of September, mid-September?
Yeah, it's really late September. We start after most universities do.
So that means you end in like mid-June, and there's like a summer session if you want to take it, which is a quarter basically.
Yeah, I believe so. But I think that for most people, like financial aid doesn't cover summers, so not a lot of people go during the summer.
So what year are you in?
This is my second year.
Second year. Okay. So if you're in electrical engineering, what is it one particular area of double E or?
No, you start out pretty like generally. In fact, this is my first year doing electrical engineering things. I was originally planning on going into something else. But in the beginning class, you start out with electrical and computer engineering, and it's a very like broad overview of the field.
Mm-hmm.
So you cover pretty much everything, and then but like at a very surface level. And then from there, you can take electives that are more specialized or
So
specialized.
does that mean you're taking like differential equations now and taking, I guess it would be like basic circuit theory and stuff like that. I'm trying to remember back to when I did it.
Yeah, it's a lot of things like that are included in the class, and then also like math classes. There's a lot of math classes early on. So I'm in calculus right now.
Okay. So differential equations is like, are you what are you in the multivariate calculus, or because there's differential calculus, integral calculus, then multivariate calculus, then differential equations.
Let me see what the full scope of this class is.
I'm just curious. I'm not trying to put you on the spot or anything. I'm just really curious, having suffered through it myself.
It looks like this class is differential and integral of functions of a single variable, analytic geometry, infinite series, and applications.
Okay. Oh, it's going to get so much more fun. I hope you like math.
I do.
I hope you like math a lot. So here's
it is really tough, but it's also like really interesting, and the graphs are so beautiful.
Yeah. Well, here's what I did not know, and I wish I had known because I wouldn't have changed anything. But here's the fact that when I was in engineering school, it turned out that I ended up 3 classes away from a second degree in mathematics, like a full bachelor's degree.
That makes sense.
That was because it was, calculus, differential equations, linear algebra, complex variables. And once you've taken all those classes, you look at it, and the only thing you have left to take is an applied math class and 2 terms of theoretical calculus to get a math degree. And I just looked at it and said, nope. I had friends who did it, and I looked at what theoretical calculus was. I'm like, I like math, but I don't like it that much. I don't like math that much. That was a bad class.
I don't know that much about theoretical calculus. What's the
It's
application?
proofs. It's all proofs.
Oh,
And-
okay.
And I looked at the coursework. I'm like, you know what? No, I could do it, but nope. No thanks.
Yeah, I'm not a super big fan of proofs either.
Yeah, I'm more an applied mathematics person, so rather than the theory of math. My father-in-law is a mathematician, so I looked at the stuff that he does. I'm like, yeah, that's all proofs. I'll do it if I have to, but I'm not going to go just study it on purpose.
Just out of the blue, years ago, I decided I wanted to learn real analysis, which is basically theoretical calculus, I guess. It's point set topology, and real analysis. And when I took it in college, I didn't get it. But years later, I looked at it and I thought, whoa, this actually started to make some sense. This is really cool. And it's actually pretty awesome. If you get into it, it's pretty cool stuff.
Yeah, and the thing is that when you're in the weeds and you have to study it and you have to regurgitate it and you have to do it for a class, it's very different. Like I look back at engineering school and I can see, 35 years later, so much of it makes so much sense.
Isn't that true?
Didn't make any sense back then. It's like, oh, that whole signals and systems class. Oh God, I get it now. How did I blow it so badly?
Isn't that the truth? It just, oh man.
How did I not understand that?
I know, it makes so much sense. So, yeah.
Yeah.
I think a lot of people experience that.
Oh, infinite impulse response. I get it, but I didn't get it then. It was the hardest thing ever. And, it was just like, because you're so deep in the weeds, you're basically, college for me was essentially 4 years of panic. Looking back, it was 4 years of just utter panic where I never felt comfortable ever, the whole time. And now,
when really there was nothing to be anxious about. But
right,
I guess when you get older, you realize youth is wasted on the young.
That's right. Hey, JD.
Hey, Scott.
Hi, JD. You want to give your spiel?
Spiel? Okay.
Yeah.
Hello, class, and good luck. And any questions?
Anyone's wondering what JD is here for, JD is going to be the lead and session coordinator for the exam session this afternoon.
Oh, awesome.
So if you have
Thank you for doing that.
If you have any questions or, like, am I signed up properly, or do I need to, if you're on the East Coast and you want to be the first person called, because we can't take everybody at once. We don't have enough people to test everybody at once. So if you need to go early or you need to go later, also to make sure that I've got your phone number in my records. So when you registered, you might have wondered, why does this guy need my phone number? This is why I needed your phone number. Because if you're going to be taking a class, I'm going to need to be calling you. So,
and I see 13 14 people on the screen and I only got 8 or 7 registrations.
Yeah, that's about right.
Uh-huh. The others are not coming? Is that what you're trying to say?
I think that's what we're saying, that they're either not going to
Okay.
take it now, or, I mean, they're all making the investment of being here, but,
Sure.
not
I want to get the
necessarily.
PO box before I take the test.
Yeah.
I'm sorry, Danya.
Oh, I just said that I wanted to get a PO box before I take the test.
Good idea.
Yep.
Why is that a good idea?
Well, because your address is associated with your license. So if you want a little more security, you can get a PO box, and then like my physical address is my mailing address. So everybody knows, if they really want to, how to find me.
Right.
I'm not particularly worried about it, but for some people, it is more of a concern.
I'm not either, but I like to say salesmen can knock on PO boxes all day and not get an answer.
Very true.
Speaking of investment, how much has JD invested in all that equipment behind it?
Oh, actually, that's not real. That's just a picture.
Man, you wish. Well, to tell you what it's all about. I was licensed when I was 14. I'm 75 now. You've seen 61 years of this business behind me. And this is my little corner of the basement.
That's a lot of equipment.
It's especially
is.
instructive if you pin him and look at everything. I see what looks like a Johnson Viking matchbox, Johnson
Correct.
matchbox, and it looks like maybe a Dentron amplifier, and is that a Yaesu 901?
No, God, no.
No? Okay,
I'm
well, I'm
not
looking
that
over on
rich.
the left. No, an FT 901. It looks like, and that also looks like a Yaesu FL 2100B amplifier.
It's a 2100B and that's a TS 850.
Yeah.
I mean a 950.
And above that looks like an 830 on the shelf.
830. Yep.
And let's see, a couple of rotators. One of them is a CDE, I think.
Mm-hmm. The other one's a ham 4.
A ham 4, and I see what looks like a Heathkit. Oh, is that a 2140 antenna tuner back there?
Yes.
Yeah, I have been doing this a long time.
So anyways.
Anyway, if anyone has any questions about this afternoon, or you need to go early or you need to go later and you're on the roster, JD, is everybody paid up and has all their agreement stuff done?
I have Russ Wilson, Dominic Wilson, Thomas Falconer, Michael Nielsen, Matthew Havner. Did I pronounce that right?
Havner.
Havner, okay. Lolly McKenzie and Megan. All paid up and ready to go.
Okay.
And I
wouldn't mind going in.
just got a payment from Joshua. I need his EA yet.
Okay, and I don't think he's here today, but I think he was signed up. And someone else was going to say something.
Yeah, it's Mike. I wouldn't mind going a bit early if possible because I'm on Eastern time zone.
Okay.
This is Megan. Can I jump in on that as well? I'm also Eastern time zone.
Yep. Okay, I'm going to make
Whereabouts
a
in
note.
Eastern are you, Megan? Michigan?
Yes, actually.
Okay, let's see. Notepad. I'm going to start a notepad thing here.
Mm-hmm.
Early. Mike, Megan. Okay.
And even though this is the Anchorage Amateur Radio Club VEC, I'm stuck in Maryland.
Yeah. Is it Lex Park or California?
Lexington Park in California is down the road from me, about
Yeah.
10, 15 miles.
Okay. So you want to hear something fun? So have you ever heard the call sign K1HTV?
Oh, yeah.
Okay. So Mike, you live in Amosville, right?
Yeah.
Did I get that right?
Yeah. Amosville, yep.
Okay, so I went to school with K1RA, who's K1HTV's son, who is Andy, a good friend of mine, and Mike lives 1 mile from Rich, K1HTV.
Yeah, I had breakfast with Rich this morning, actually.
Did you say hi for me?
I did.
Oh, cool. Yeah, he's a nice guy.
Lovely fellow, yeah.
Good operator too. Really good operator. All right.
So the main thing is don't be nervous.
Nope.
Take your time. There's only 35 questions on the test. And probably take you all of maybe 15, 20 minutes, unless you're a speedster like some people are. We've had people go through it in like 6 minutes.
Or if you're like to double check everything, in which case it might take half an hour.
When you get to the end of the question list, don't hit that little button down in the corner that says finishing grade unless you're absolutely sure. You got the chance there to go back and review your questions. And as like everybody likes to say, don't second guess yourself. If you took a question that said, answered the question like you thought that was the answer, leave it alone.
Yep, it's probably right.
Statistically, 85% they say your first impression is correct. You only need 26 to pass.
Yep,
26 out of 35.
73% score. You got to get a good solid C.
That's
All right.
not all there is to it.
Anything else, anyone? So we're going to start at 2 o'clock Pacific time.
Mm-hmm.
That'll give people a little bit of time to practice and eat some lunch and, go to the bathroom and relax a little bit.
Take care of necessities.
Take care of necessities.
And Scott will be the gate guard. He'll call you individually depending on what kind of a list he gets of who has to go first. We'll bring you in, get you ready to go into a testing room with 3 other people and get this done.
Yep. And you
I have
need
one question.
Yep.
Yes, sir.
If I used my physical address and I want to change to my PO box, would I do that at the FCC page?
If you can get into the FRN page right now, change it, yes.
Okay. I would just do that by managing my FRN.
I'm sorry, what was the question again?
Whether or not you just manage my FRN.
Yeah.
Okay. Yeah, I think I can update. Yep, I found it. Thank you.
Good.
I have a similar question about my email. I feel like I wound up with different emails being used different times. And I know that that's one of the big things that needs to be consistent is the email. Should I check that?
Yes, please.
In the same place? Okay.
And we can also look at it when you go into the test room on what they call the 605 form. It's one of the first ones you're going to see. You
Okay.
can say my email is wrong. We can change.
Okay. All right. Because I realized I was doing some things using my school email because it was officially related to school. But then I realized that long term, I don't want that to be the email associated with it.
That's an important point. Make sure your email is correct.
Okay.
This is the only way the FCC is going to communicate with you. If they don't use mailing addresses all that much anymore. If they can't find you, the first thing they want to do is try and cancel your license on you. So keep your email current. Anybody else? I'll see you all in a couple hours and good luck.
Thanks for dropping in, JD.
Talk to you later.
All right. Well, let's get back to this. And we lost somebody, but I don't know who. Hopefully they make it back. All right. Continuing right along. We are now into rules and regs. Okay. The organization that is part of the United States government that runs amateur radio in the United States is the FCC, Federal Communications Commission. Okay. Now, if you go to the FCC website, you can find this. I will also point out that we have an organization in the United States, which is our member society, sort of like IEEE for engineers or whatever. and it's the ARRL, which is the American Radio Relay League. All right. Now this is my little advertisement for the ARRL. The ARRL is our member services organization. There are about 800,000 hams in the United States, and about 160,000 belong to ARRL. So if you're a member of ARRL, basically you get to use their functionalities, their privileges. You get to use the QSL Bureau and things like that. But more importantly, notice it says the National Association for Amateur Radio. They are our voice in Congress. They are our voice at the FCC. So if you like using the frequencies that we have, please keep in mind that those frequencies are under constant attack from commercial entities that have financial means at their disposal, like a lot of money and a lot of lawyers. And how much money does the FCC make from ham radio? Virtually zero, right? So we are a non-commercial service. We are something that doesn't make any money, and it doesn't earn any money for them. What we give back is the fact that we are the people who understand and promote and use technology for education, for public service, for scientific discoveries, for all kinds of good stuff. But that doesn't mean that our frequencies are not coveted by a lot of different organizations, a lot of different companies, a lot of different services. And sometimes, as we will see in just a minute, sometimes we will lose frequencies. Sometimes we will have our frequency allocations cut in half on a certain band. Sometimes a certain band will completely disappear from our list. So the ARRL is basically the group that represents us in front of those agencies and says, look, we're doing all these good things. You can't take our frequencies away. So independent of the fact that they're a publishing house, they organize clubs, they organize exam sessions, they organize contests and activities. They are also a lobbying organization for our benefit. So it is a good idea to be a member of the ARRL for that one reason alone if you happen to enjoy ham radio. Anyway, that's my little spiel for the ARRL. So here's the FCC. The ARRL talks to the FCC on our behalf. Now, one thing that is on the ARRL website and on the FCC website is Part 97. Part 97 is the rules regarding ham radio. That includes basically the 5 reasons for us to exist. At the very beginning of the rules is the basis and purpose of the amateur service. So if you're wondering what in the world it's actually there for, I can bring up FCC Part 97 text. Okay, I'm going to bring up FCC Part 97. Here we go. This is it. This is the FCC rules regarding amateur radio. It covers everything that we are and are not allowed to do with our licenses. That's a lot of stuff, right? At the very beginning of this, however, is basis and purpose. This is why we are allowed to exist and why we have existed continually for, as a group of experimenters for over 100 years and continue to do so, because there is some benefit that we provide. So you don't have to memorize these. Value of the amateur service, continuation of the ability to advance the radio art, single sideband, the thing that we call single sideband, which is still the most prevalent mode of analog communications used today. That came about as a result of hams who saw something in AM that they didn't like and said, we can do better. Rules that provide for advancing skills in the communication and technical phases of the art. Expansion of the existing reservoir of trained operators, technicians, and electronics experts. A lot of the technology that comes out is very high tech, right? By virtue of us existing, one of the goals is to continually expand the pool of people who know what they're doing. And finally, international goodwill. Believe it or not, There are no countries that we are presently not allowed to talk to. I have a stack of QSL cards from when I was in high school and college from the Eastern Bloc, you know, from East Germany, from Czechoslovakia, from the Soviet Union, from Romania, that was part of the communist bloc, all the Baltic states, Poland, that we were not on particularly friendly terms with. But the hams could always talk with them, and vice versa. They could always talk with us. So, international goodwill, a non-commercial service that supports international goodwill. We still can't talk with North Korea, but not because we're not allowed to, just because they don't have any hams there. Okay, so advancing skills in the technical and communication phases of the radio art. That's one of the ones that's actually the one that will show up potentially on your exam. A beacon. What is a beacon? It's an amateur station for transmitting communications for the purposes of observing propagation or related experimental activities. Part 97 definition of a space station. A space station means that it's at 50 kilometers or higher up. Hold on a second. Okay. When is willful interference permitted? That means basically you are intentionally interfering with another station, even if they're pissing you off. The answer is never. A group that recommends transmit and receive channels and parameters for auxiliary and repeater stations. That is known as the Volunteer Frequency Coordinator. The Volunteer Frequency Coordinator is selected by hams in a local area whose stations are eligible to be repeater or auxiliary stations. In Oregon, we have something called the ORRC, if you are curious. If this comes up properly, and here is the ORRC. One of the things that the ORRC board does is that they establish repeater channels, and they assign them to people who apply for them. So in the state of Oregon, this is a list of all the repeaters that have been coordinated, and geographically they've been selected so they don't interfere with each other. So you can actually, for instance, you can have a repeater on one frequency in Eugene and another one way up in Astoria, which is true, and another one over in Bend, and they don't interfere with each other because they're far enough apart. This is the organization that handles that kind of thing. Okay, frequency allocations and power limits. So this is where it becomes really important to look at this chart. Frequency allocations and power limits. What frequency is in the 6 meter amateur band? Well, we can look at 6 meters. This is just one of those things you have to know. It runs from 50 to 54 megahertz. So if we look at this, we will see, oh, there's 49. That's pretty close to the 6 meter band, but it's not in it. 52525, that's actually the FM simplex calling frequency, so that is the answer. What band includes 146.52 megahertz? You can come back over here and see that 146.52 falls squarely in the 2 meter band. We can also use our math and figure that out.
Or you can come at it another way and recognize that 14652 is the 2 meter calling frequency.
Correct. Exactly right. On what HF band does a technician class operator have phone privileges? Phone is another way of saying telephony or voice. And you'll see that novice technician voice is this blue hatch. The blue hatch exists on the 10 meter band. So as a technician, you can operate on the now very, very exciting 10 meter band because we're getting up to a good spot in the sunspot cycle. So you are allowed to do voice DXing on the 10 meter band. Frequency ranges available for phone operation on the 10 meter band, 28.3 to 28.5. Where can SSB phone be used in bands above 50 megahertz? Well, we can look at that, and we see SSB, and there's that little pale green. Look at that. It exists on every band. So what that means is that at least in some portion of every one of those bands, you can use single sideband for long distance contacts. Which of the following VHF UHF band segments are limited to Morse code? CW is Morse code only. Well, we can see that CW is the red area. So we have 50 to 50.1, 144 to 144.1, and 222 to 222.1. The only answer here that's right is that it's on 6 meters and 2 meters. Okay, so when I say that we are constantly under attack, our frequencies are constantly under attack, I want everybody to notice this. How may amateurs use the 219 to 220 megahertz segment of 1.25 meters? So we're going to go over here, and what do you notice on 1.25 meters? Where does it start? 222, right? And it ends at 225? Well, where in the heck is 219 to 220?
Gone.
No, it's not gone. What happened was this band used to go from 220 to 225. It was 5 megahertz wide. And an organization known as United Parcel Service came in and said, we have a proposal to use the 220 to 222 band for our remote package tracking systems. You know, those tablets that they punch, that you sign and punch information into? We need 2 megahertz. So they said, okay, hams, what we're going to do is we're going to take away those 2 megahertz and we're going to give you in return 219 to 220. But you can only use it, instead of the way you want to, you can only use it for fixed digital message forwarding systems. It's like, how weird is that? This is a direct result of a commercial, we'll call it an attack. Basically a commercial application that somebody came up with to swap out frequencies. So what ended up happening was we had 2 additional megahertz of space that we could use that we essentially lost and was replaced with something that we really hardly use at all due to commercial needs. So that's what that weird little 219 to 220 segment is used for. Fixed digital message forwarding systems only. That's it. We can't use it for everything we want. Why should you not set your transmit frequency to be exactly at the edge of an amateur band or subband? Okay, this is actually really important. The FCC specifies, for instance, that let's say the 2 meter band goes from 144 to 148 megahertz. That doesn't really tell us how to use those frequencies. It just says that this in here is your area to play in. That's your sandbox to use any way you want. So if you pick a frequency that's at, well, let's say 144.000, and you pick it right here, your signal that you transmit is going to have sidebands. Well, what do you notice about the right-hand sideband? The upper sideband, that's okay. How about the left-hand sideband?
No bueno.
Nope, because it's outside of the band. It actually falls outside of the window. So, that being said, what this really means is that we don't want to, number one, put our signal right at the edge of the band, because if we do that, some of our signal is almost guaranteed to fall on the outside. Another thing is that, let's say we were to pick up here and our transmitter drifts a little bit as it warms up. Oscillators do that. And what was normally, if everything was fine in the band, has now drifted a little bit, and it's now out here. So it's drifted because of things warming up and temperature shifting and stuff like that. It's now gotten to the point where it's outside of the band. So that's another reason to not be too close. Another reason to not be too close is that your equipment, if it says 144.300, or sorry, 0.003, Well, okay, if everything is right, your signal is going to fall completely in the band. You put it right here and it's right here. But what if your frequency counter, your calibration, is off by 1 kilohertz? You're actually right here. You think you're fine, but you're actually not. So we try to leave a little bit of room on the edges to account for, inaccuracies, temperature drift, frequency drift, things like that. Okay. Okay, next. How are U.S. amateurs restricted in segments of the bands where the amateur service is secondary? This is a very, very important thing. We are not always the primary users of a frequency. Sometimes we are secondary users. If we are secondary users, that means that somebody might show up that actually has a higher privilege to be in that band. For instance, the entire 70 centimeter band from 420 to 450, we are actually secondary users to the U.S. military. So they have, if they need to, the right to say, you guys can't be here, and can actually kick us out temporarily. We need to use this band exclusively. You need to stop. Fortunately, that doesn't usually happen, but it could happen. So we need to not interfere with them. Sometimes if we're secondary, like on the 30 meter band, we're secondary and we're being permitted to be there. But if somebody else is there, we can't say, oh, these stations are really annoying me. Well, actually, since we're secondary, they're probably the primary users, and we have to take the interference that they're providing us, not the other way around. For the most part, we are allowed to operate at 1,500 watts of RF power output, which is a lot of power. On HF segments of the bands, you're allowed to operate at 200 watts. Most people don't even have a 200 watt transmitter. Even if you go and buy something today, it's typically a 100 watt transmitter on HF. So in order to get anything higher than that, you're probably going to be dealing with an amplifier, and so this is never really going to be a concern. So above 30 megahertz, 1,500 watts. If you have a technician class license, it's 200 watts on HF. All right, license classes. License classes that are available from the FCC. Notice that this says Technician, General, and Amateur Extra. No, I don't know why it's called Amateur Extra as opposed to just Extra. Similarly, I don't know why the other ones are not called Amateur Technician and Amateur General. They've never been called that for some reason. So, Technician, General, and Amateur Extra. Now, notice up above, there's something called a novice and an advanced class license. These licenses still exist, but you cannot be given one right now and have not been able to get one since like 1994. But they haven't been grandfathered into anything else, which is why they still exist. The normal term for an FCC license is 10 years. So it used to be that when you passed an exam and you got your license, you would wait for something to show up in the mail. The mail is no longer the definitive thing saying you have a license. What is the definitive thing saying you have a license is the FCC ULS database, or Universal Licensing Service, Universal Licensing System. So, for instance, we're going to go to the FCC ULS. Okay. FCC ULS license search. Here we go, amateur license search. I'm going to type in my call sign. Even if I don't have something on paper, if I go into this database, there we go. N7JI, Rosenfeld Scott R. Here's my FRN. I am active, expiration date 2028. If I drill down, I can see details. I can see the entire history. If my license is in here and it says active, then my license is valid. You don't have to wait for anything to show up on paper. It's just that if it's there, it's there. That's the ultimate decision maker as to whether or not you have a license or not. You do not have to wait for anything to appear on paper. If the FCC processes your license and it pops up in the database, it becomes valid. You can operate as soon as it shows up. You can have, as a person, you can have one operator and primary station license grant. What proves that the FCC has issued a license grant? The license appears in the database. Who can apply for a vanity call sign? That means a call sign of your choice. It doesn't necessarily have to be your initials. Anybody who is a ham can apply for a vanity call. So license classes and call signs. Every United States call sign is going to have one number in it. It's then going to have a prefix, which starts with a W, an N, or a K, or an AA through AL. And it's going to have a suffix, either 1, 2, or 3 letters. So as an assigned call sign, you're going to have at least a total of 3 letters and 1 number. It can be in the form of KA1X, for instance. That would be a 2x1, as it's called, or W1XX, or in this case, KF1XXX. Now, it's important to note that a technician class license will only be in the format of 1x3 or 2x3. So W7 CRM, W7 TBS, KA7 OML, KA3 JTW. Those are 1x3s and 2x3s. As a technician, that's all you can apply for. That's all that's all you're going to get. If your license expires, you have 2 years grace period. After 2 years, you have to retest. If your license expired and it's still within the allowable grace period, you can say, oops, I forgot, and send something in. But until it shows up in the database as renewed and active, you can't operate yet. Any club has to have 4 members to get a call sign and a license. When can you get your station operator license revoked? If the FCC tries to send you something through email and they can't find you, it gets bounced, they can pull your license. From which of the following locations can an FCC licensed station transmit? From any vessel or craft in international waters or documented in the United States. So, I also saw that Andrew, are you here? Oh, he popped in.
Yes,
for a minute.
I am. Sorry.
Oh, there
if
he
I
is.
could unmute, I would be good.
Yeah. Danae, hey, are you still there, Danae? Danae, can you pick up? She might have walked away.
That's fine.
Oh, wait a minute. There we go. Okay. You're muted again. Danae, we can't hear you.
Sorry, my signal just dropped.
Okay.
I lost the
So do you guys know each other?
No,
Andrew?
who's Danuya? Denaya? Sorry.
Andy and Woo.
Andy. Oh,
Andy.
No.
Okay, so there were some questions about ORSAT and the fact that we now have, and I'm going to pull this up. Let's see, AMSAT tracker, ISS tracker. Okay, so the fact that you guys have a satellite up in space, and there's this AMSAT satellite tracker. Oh, God, I don't know why it's on Bing. Okay, so the fact that I can actually go down here and I can pick ORSAT 0. And from CN84LA, the question is, how does the linkage between you guys and AMSAT work to the point where they have access to all the orbital elements for the satellite that you put up?
That's a really good question. We have no control over it actually, which is interesting. If you go, well, the first thing is it starts with 18th Operational Space Group out of somewhere in California, I don't remember where, sorry, who has giant radars across the world, millimeter radars. And what they do is they continuously nuke the night sky, looking for anything larger than about a six-sided dice. There's some conjecture that they can see things that are smaller, but they won't say anything less than about a quarter U CubeSat, which is about 10 by 10 by 4. So that's what they say they can do, but we know that they can actually do smaller down to about dice sized, and maybe even smaller. Anyway, they map the night sky every day. Literally every day. They're constantly scanning for low and medium Earth orbit. They might be doing geosync too, we don't know. And their job is to catalog everything in the sky that can be cataloged. So if it's not a black satellite, a defense satellite, or it's not some other nation's defense satellite, then it's in the catalog of everything that's up there. And every 2 days, they update what's called the two-line element, or TLE, of every known object. And when we deployed off the Astra 009 rocket, they actually tracked a constellation of stuff that kind of came off that rocket. There was us and 12 other satellites, and nobody knew who it was. So for a while, it was like object, this date, -1, -2, -3. We thought for a while we were -17. It turns out we were -19 or whatever it was. And then they gave us a number, and then that number goes into the database. So if you bring up celestrak.org.
Celestrak?
Yeah, CELESTRAK.org. This is a guy, a very famous guy, who takes all of that data in and publishes a beautiful 3D rendering of where all the satellites are on the planet, and you can go and particularly choose 1 or 2.
Oh, it's
Yep,
a
that's it.
nonprofit. Okay.
Yep. Yeah, he's a great guy. Kelso, T.S. Kelso. So go to I think it's SatCat. So search SatCat down below. And then name ORSAT 0. Yep. And then submit.
Oh, there it
Yep,
is.
there it is. And so there is our NORAD catalog number. We're 52017. The FCC has published. We never even talked to the AMSAT actually. We just get published in FCC as we're using radio Part 97, and then they associate that with the NORAD catalog number, and we're thus an amateur radio satellite, which is great. I mean, we did talk to them and everything, but we didn't have to do anything. And where's the map? That's the really fun thing to look at. Click on the thing off to the
latest data.
Oh, there's the
there's
two-line
two-line
element.
elements.
Yep. Mm-hmm. And I could spend a week trying to tell you why it's a two-line element and why the 1960s still has its revenge on us, but we don't need to go there. Click on the little link next to 2022-026K off to the left. Yeah, click that. No,
Looks
okay.
like two-line elements forever.
Oh, this is interesting. This is actually everybody who got launched with us. So this was our launch.
Oh.
And so you can see Space
Yeah.
Bees. There were lots of Space Bees from, I forgot the name of the company that launched with us. Those are quarter U satellites.
Cool.
Yeah, so it's, let me see if I can find.
Here, are you talking about this?
All right, let me unshare and let you. Okay, go ahead.
Oh, you can go there. Let me, if you don't mind sharing
Go ahead.
me sharing my
You
screen.
should be able to now.
Okay.
I hope everybody's okay with us taking a little break to see this.
Yeah, this is cool.
I can do it. I know I can do it. Look, I did it.
Well, you did something.
No. Or is that
You look like you're at home today. Are you okay?
Thanks. So if you go to orsat.org, you go to satellites and click on ORSAT 0. You're a jerk. Oh, there it is. Sorry, their dashboard is on the main thing. And then you can look, this is an internal thing. I think Danae, this is what you were pointing to. This is our own version of something called cesium, which is a 3D rendering. And so right now, if you look at where we are off, I forgot That's not Seychelles, is it? No, I don't remember.
You're
That's Africa.
Yeah, you're down off
Yeah.
the Falklands. That's the
Falklands.
Well, the Falkland Islands are to the west. You're like around by the
Yeah.
South Sandwich Islands.
Yeah, okay. I have no idea. I'm bad at this. So there you go. So
You got
there's
to
our
do
set
more
zero where we are
DXing.
right now.
If you do more DXing, you'll know all these islands.
It's totally true. Oops, all right, I can't run this one. So anyway, so this is based off the two-line element. So it's not a real-time position. It's just using the TLE. And the TLE is good to like a couple kilometers for a 24 hours. And then let me show you.
So what's the altitude of Orsat 0? We were talking about that.
Oh, that is a good question.
Well, I noticed that its pass length is a little longer than I'd expect. So it's probably 240, 250 miles, something like that.
Oh, that's sad. Okay, so they actually, sorry, you can't go to Celeste Track and show the pretty picture. So this is as good as you're going to get. They stopped that service. Anyway, we don't know. I would have to go back to the two-line element. I would have to recalculate what the orbit was. The last time we checked, I think we were at 515, 510.
That's kilometers.
Kilometers down from 525 where we were originally dropped off.
Okay.
Yeah, so we've not gone down a lot. It's an exponential
So that's
decay.
about 310 miles. Okay.
What miles? What are miles?
Yeah, I know.
We don't use miles. So yeah, it says 300-ish miles. And what's going to happen is we'll be at 300 miles for quite a long time, where we'll be slowly coming down. And then eventually you'll see this knee happen and we'll start to plunge in. And then by the time we get down to about 200, 150 kilometers, then we become a meteor shower.
Yeah. And that's because of air resistance causing drag, slowing you down.
That's exactly right. Yep.
Yeah.
Yeah, even up at 525, even up at about 700 kilometers, you'll still deorbit. In fact, when people tell you that space debris is a problem, it is a problem, and it's a serious problem, but it's not really a problem under about 400 kilometers. So when you get in this real low 500, 400 kilometers, in 5 years, everything deorbits and burns up. So it's kind of an okay place. The problem is that the space station is down at 430.
Yeah.
And so we're above the space station, which gives us a little bit of nervousness. I mean, they'll move. They've got weeks of warning. They have precision orbital estimators that go out weeks instead of days, and ours are just days. So
yeah, I know it's pretty cool. And actually, interestingly, when we are dealing with, we talked about F-layer propagation yesterday. The F-layer propagation is between, let's say, 250 and 500, 600 miles up. So,
oh, I didn't realize it was that low.
Yeah.
Okay.
We're actually, using ionization in the atmosphere around the level of these satellites. So, there's clearly atmosphere up there.
Yeah, that's fascinating.
Yeah.
Yeah, interesting.
So do you have a prediction of when your satellite will burn up? And are you going to try to bounce a signal off the ionization trail?
I wish we could.
It's a little satellite.
So the answer is no, we're not even trying. And you get in trouble when you try, because people who are defense people get very, very, very nervous when you start to try and predict reentry. That's not a thing that us mere mortals do. So we'll be able to track it, and we'll be able to see it, kind of predict when it's going to come in, but we probably won't know where. We won't have an updated thing. If we had our GPS turned on and we were broadcasting our GPS coordinates to SatNog stations around the world, we might be able to predict where it's going to come in. But again, they get nervous. We probably won't do that. So, but we'll know within a day when it's going to come in. And we originally predicted in 2019 that it was going to be 5 years in orbit, but the new sun models have expanded our atmosphere. And so it's probably going to come down more like 3 or 4 years. So.
Cool. Other questions for Andrew before we go back to finishing up our class?
Well, since we're talking about amateur radio, can I show you guys some cool things?
Yeah.
Okay, hold on. So one of the things that happened,
and just so everybody knows, we'll probably be done by 12:15. So again, I hope everybody's okay with us extending it just a little bit for We'll call it enrichment activity.
Yeah, kick me off for sure. Okay, I'm going to do this. I'm going to share my screen again. So for those who don't know, Orsat 0 is a flawlessly built satellite that works incredibly well. Can't believe how well it works.
It didn't catch fire.
It did not catch fire. And part of it, though, is it does have its problems. And the problem is it can't listen to us. It's got a problem with the low noise amplifiers in both of our radios. We have a 1.2 gigahertz uplink and we have a 430 megahertz uplink, both of which can't hear us. One is actually jammed with an oscillation in the low noise amplifier, and the other one has the low noise amplifier turned off because of a firmware bug. It's so embarrassing. Anyway, this is myself and Glenn. Glenn is KJ7SU, and we are in a hotel in Stanford trying, this is a model, an engineering unit of the satellite. And these are power amplifiers, and we are trying to get a last minute thing to work before we go to this place. This is the Stanford dish down in Stanford, California. And one of the things we realized is that if we had enough gain, we could get past the fact that the low noise amplifier was off. How much gain? Well, a 40 meters worth of dish gain. So it turns out that this thing has a 40 dB gain, and I think that's a factor of a million or something.
10,000. 40 dB is 10,000 power. Yeah.
Okay.
We covered that. We never got up to 40 dB though.
Yeah, it's funny that. And what's really cool is you can see these little wheels here. This whole thing, including this house right here, that whole thing rotates with the antenna. And so there's the dish from far away. And excuse the History Museum pictures for a minute. That was a cray. So there's the feed horn antenna up in the where the dish focuses, right? And that's a 100 megahertz antenna and a 400 megahertz antenna right there. And skip all that stuff. There's Glenn. It was we got to go up in the antenna, which is really cool and interesting.
When it was not transmitting.
Yeah, thank you. Yes. And you can see here, it's a mesh, right? Because they don't care about anything past about, I think it's 10 gigahertz. And so this mesh is fine enough for anything up to about 10 gigahertz.
Which is the same reason that your microwave oven, you can see into the oven and the RF doesn't get out.
So this is amazing. This is a coaxial cable that's a megawatt class rated. And what's really interesting is it rotates right in here. So this is a megawatt class rotator for coaxial cables, which is insane. That's their rotator. That's the secret shack where the CIA goes to use their antenna. Nobody knows what happens in there. And I think that, oh, here's a quick movie of the thing actually moving. Give it a second. So they're getting ready for a pass of Orsat 0. And it was actually amazing. We asked if we could use the dish on Thursday of like about a month and a half ago. And on Friday, they said, yeah, can you come down Sunday? So we cruised down there and got to use this amazing dish. And they were ham radio operators, and they'd done other CubeSats before, and it was really cool. So neat stuff. Anyway.
Very cool.
And we got to it. We actually talked to the satellite, and it heard us and responded. And it was awesome to hear that we actually were still working up in space.
Very cool. Right. Andrew, I'm glad you could drop by.
Yeah, my pleasure.
Yeah, thanks for that. That was really interesting.
All right. You guys ready to go back to class? We're almost done. All right, here we go. Thanks, everybody. All right, so we are back onto this. We are on page 115 of 127. It's actually closer to the end than we think. Okay, authorized and prohibited transmissions. So language that is indecent or obscene is prohibited. The only time we're allowed to transmit music, because we have music stations that can do that, is when we're talking to a manned spacecraft. Typically, that was the space shuttle, when we would retransmit music that was wake-up music for the astronauts. When are you able to transmit messages that are encoded to obscure their meaning? We are allowed to use codes and ciphers and things like that, so long as the decode key is available publicly. When we're controlling radio control craft, such as drones, or space stations, anything above 50 kilometers, we're allowed to encrypt our messages, because we don't want anybody getting in and hacking our satellite and causing it to deorbit and crash. Who are we allowed to talk with? Basically, anybody if their country has not said we're not allowed to. When are we allowed to make money? Only when you happen to be a teacher and you're using it as part of your classroom instruction. So you're still allowed to collect your salary, even if you use ham radio on the air when you're teaching. When can you use a radio to notify other people, other hams, of the availability of ham stuff for sale? Basically, you can't run a business on the ham radio, but you can say, oh, you know, we have a swap net going on. I've got a radio to sell. You're allowed to do that. What is broadcasting? Broadcasting is meant for the general public. We do sometimes one-way transmissions. One-way transmission is like broadcasting, except that one-way transmissions are designed for the ham radio community. Broadcasting is designed for the general public. We're allowed to actually participate in news gathering, news production, and things like that, which is kind of an obscure thing, but only basically this is helping out news, like a TV news channel. When can you help out? When can you send messages? Again, we come back to if your cell phone's not working and there's no other way of doing it, and we're talking immediate safety of human life or protection of property. If you see an answer that is immediate safety of human life or protection of property, that is probably the right answer, because those are the times when we are allowed to violate the rules. So what can we talk about? We can talk about anything that is comments incidental to the purposes of the service, and remember there were 5 of them, or remarks of a personal character. I used to laugh at the fact that people would get on the air and bellyache about the fact that my sciatica is acting up so much. I can't wait until I get to go to the doctor next week, and things like that. Well, now I'm not 18 anymore. I'm 53, and man, I do have sciatica. And you know what? That is important. That is a significant thing. And I do have a doctor's appointment next week, and I am talking about that. So it's fun. Those are comments of a personal character. Okay, when can an amateur station transmit without a control operator? A control operator is the person in charge, and the answer is never. Even if it's an automatic station, the control operator is the person who is licensed to run that station, even if it's not running automatically. The control operator of a station, unless there's something in the records that says otherwise, is the station licensee. The person who is licensed to have that is their station is ultimately responsible. So who must designate the station control operator? That's the station licensee. In many cases, these are 2 different people. In more cases, these are the same person. I'm the licensee and I designate myself. I'm the operator. When these people are different, so let's say that the station licensee is the trustee of a club. Well, as the trustee of a club station, the person who is licensed as the club station trustee, which in some cases is me, I am a club trustee as well. I'm not going to be the control operator all the time. If something goes wrong there, we are both responsible for it. If a repeater inadvertently retransmits something that violates the FCC rules, somebody gets on and starts cursing or playing music, I'm the trustee of a repeater. Ultimately, you would think that I'm responsible. Actually, I'm not, because it's an automatic thing. The person who initiated the communications violating the rules is responsible for it. I might take it upon myself to shut it down, but I'm not responsible. Can a technician class licensee be the operator of a station operator operating in an amateur extra class band segment? If you look at that sheet of all the frequencies, you will see that that is not permissible. Notice it says under normal circumstances. So what would be not normal circumstances?
Threat of life and property.
That's right. There it is. Threat to human life or protection of property. So When those things are true, all other things go out the window. Assuming no other means of communication is available that is legal. So who can be the control operator of a station communicating through an amateur satellite or space station? Basically, if you're allowed to put a signal up on the uplink frequency, it doesn't matter where it comes down, even if you don't have privileges there because you didn't put it there. So basically what that means is you're allowed to transmit where you're allowed to transmit. An amateur station control point is where the control function is performed. In the case of this amateur station, which is a handheld radio, this push to talk button is the control point. Remote control, I actually can control my radio remotely from this computer, which is not in my ham shack, over the internet. That would be remote control. For remote control operation, the operator has to be at the control point. If you leave the control point, you have to break the link. The control operator has to be there at all times. And the control operator indirectly manipulates the controls. I can tune, using an interface, I can tune my radio from this other computer. Okay, repeater operation is a perfect example of automatic control. Station identification, repeaters, third-party communications, and FCC inspection. Okay, this is it. This is the end of the whole thing. How often do you have to how often do you have to send your call sign? Every 10 minutes, and when you're done, at the end of a communication. There's only one time that you're allowed to send a signal without identifying it over the air. That would be if you're running a model craft, model airplane, model boat, something like that. You're allowed to transmit 1 watt if you're doing that, and your transmitter has to have all your identifying marks on it: call sign, name, address. If you're operating a phone subband, you can speak any language that you like. You can have a Spanish conversation. In the United States, you have to give your identification in English. You're also allowed to send Morse code to identify your station when you're having a voice conversation. So there's a phone emission, that's telephony. So if you want to identify your station, you can send either Morse code or voice. Phonetics are encouraged because they increase intelligibility, especially when conditions are lousy. Tactical call signs, race headquarters. Sometimes you will be doing public service. Emergency Operations Center, Aid Station 2, Checkpoint 3. You can call yourself that. How often? What do you actually have to do? Every 10 minutes and at the end of your communication, you have to give your actual call sign. You can call yourself anything you want with a tactical call sign, but you still have to give your official call sign every 10 minutes and at the end. You can, for instance, add /3, indicating you're in another part of the country. So let's say you're from Alaska, KL7CC, KL7CC stroke, slash, or slant, W3. Those are all ways of identifying that you're something else. Third-party communications. All right, so we brought this up briefly. How somebody mentioned a phone patch. The person who is on the telephone and you are rebroadcasting, retransmitting over the air, is a third party. Now, there could be a third party on both ends, in which case 2 unlicensed people are talking to each other over the radio with 2 licensed hams running the radios. So ultimately, you're responsible for whatever goes out over the airwaves. So a third party communication, whether it's spoken by the person or on behalf of that person, is a message from a control operator to another amateur station on behalf of another person. And it is also true that within the United States and Canada, third-party rules are always okay. Third-party communications are always fine. Between the U.S. and other countries, there is a rather lengthy list of countries that do and do not allow us to have third-party communications. So you need to check the list before you do that. And finally, if the FCC knocks on your door and says, I'd like to come in and look at your equipment, we believe that it may be interfering with air traffic control, You have to let them in. That's part of the deal of being a licensed station. And that's it. That is everything. That is the whole thing.
Just one question. That last question mentioned station records. What station records do you have to keep?
You are really not obligated to keep any station records. I keep a log. A log will help if the FCC says, we see that there was interference, and if you can show that your station, you weren't transmitting at that time, that station log can help to say, oh, it wasn't me. So it used to be back in the 1950s that you had to log every emanation coming from your station, independent of what it was or how long or short it was. So if you transmitted to tune something, you had to mark that with the on time and the off time. And those logbooks filled up awfully fast. If you called CQ and nobody answered, you had to mark that down. It was quite burdensome. And looking at some logbooks from that era, you realize that it was a lot of work.
Yeah, I can imagine.
Yeah. Other questions or comments? Or thoughts? Anything?
One bit of side business. Is Matthew still in the room?
Yeah, I'm here.
Earlier in the day, you said you schedule outdoor adventures. I'd like to get in touch with you.
Yeah, sure. I'll drop the link in the chat.
Cool. Thanks.
Scott, I had a couple of questions.
Yep.
I think these are probably, so the terminology W3 and 73.
Mm-hmm.
W3 means that you are not where your station is.
Typically, yeah.
Okay. And 73, I'm assuming, means I'm done.
Well, it's actually best regards.
Best regards. Okay.
Yeah. Let's see, call sign area map. Here we go. So here is, I'm going to put this up. Hopefully this comes up. Call signs in the United States. There's amateur call signs. And that's how I knew when you said that your dad had a KP2 call sign that I knew he was in the Virgin Islands at some point.
Right. Okay.
Because you notice USVI is KP2.
So is that violated when you do your fancy one when you choose it? Do you have to follow that?
you actually, back in the olden days, whenever you moved, like if let's say you moved from Chicago to Michigan,
mm-hmm.
right? You went from 9 land to 8 land, you were actually issued a new call sign.
Wow.
So by
sounds complicated.
Yeah, well, yeah, it was a lot of work. And and they just wanted to make sure that everybody was following, that standard pattern. And eventually it was determined, we're using up call signs pretty fast like that. People move all the time. And so then it was just recommended at some point that if you, for instance, when I moved from Maryland, I was NF3I. I moved to Oregon and I could use my call sign, but more often than not, I was NF3I/7. Eventually I got tired of doing that and I found a good call sign in 7 land that I liked. So I just applied for it.
Okay.
But
so
now
the 3 was an indication that you were in
Maryland, DC.
In Maryland, DC.
Yeah.
Okay.
But similarly, like let's say that I live in Oregon and I find a call sign that is available and it's K4SR, which are my initials.
Mm-hmm.
I could apply for that. I don't have to live in that region.
Okay.
It can cause some confusion, on the air. But we've got several 4 call signs here in Eugene who are, who have relocated and may or may not ever decide to change their calls.
What do you mean by apply for a call sign?
So the same thing if oh look, the FCC ULS thing. Okay, so once you have a license, when you pass your test, you're going to be assigned a sequentially allocated call sign. So right now, if you have an address that's in Oregon, any of the 7 areas, it's going to be probably a KK7. So whatever they're up to, it'll be like KK7M something. But because of the technician license class, right? A technician license class holder can hold a 1x3 call sign or a 2x3 call sign. So that would be like K7ALP or NA7TCW. So this would be like, it would be 2x1 or 2x3 or 1x3. So if you find a call sign, like my initials are SRR, if I had a technician class license and I found that N7SRR was not assigned to anyone and hadn't been for 2 years, I could put in for a vanity call sign, pay my $35 for applying for, a license processing fee, and apply for N7SRR. And if it's available, then I'd get my call sign changed to that. Of course, I like my call sign, so I'm not going to change it anytime soon. Now, the thing is, like, if you have and that's the same license, the same call sign classes are true. They hold true for technician and general. If you happen to have a novice, you could only do a 2x3. If you have an advanced, you could apply for a 2x2 in addition. So KA7AR. An advanced class licensee could apply for that. If you have an extra, you can apply for any of the above, or a 2x2, or a 1x2, or a 2x1. So I have N7JI. It's one of the privileges of upgrading your license is that you can get a shorter call sign. The other privilege to upgrading to extra is that when you travel, an extra class license is equivalent to the highest class license in virtually every country you go to in the world. And most of them have reciprocal agreements with the United States. So if you go to another country and you have an extra class license, you basically are given full privileges to operate in that country. You just have to, some places you have to apply for a reciprocal license. Some places you just automatically have it. And you just get on the air from other countries. Any other questions? Those of you who are taking exams, feeling pretty comfortable? It's a lot of material, but hopefully, you've been doing some practice exams and feeling pretty okay. And the other thing is, if you aren't scheduled to take an exam yet, keep going on the practice exams. Keep going on, making sure that you stay comfortable. And if you get to a point where you're like, I just don't know the answer to this one, feel free to ask. Everyone's got my email address. Everyone's got my phone number.
I'd like to compliment you on how well the classes run and all the extra information. Thank you very much.
Thank you. I'm going to actually hit stop.